Hello, everyone, and welcome to the Builder's Workshop. My name is Nathan, otherwise known as Zone Build and Builds, and we have Shawn Calderon here with us, and we also have the Benefactor, and we're going to start with Shawn today, and we're going to go over some cool stuff.
Hey, thanks a lot, Nathan, for having me on. I always have a blast either in the chat or sharing some of my crazy ideas. So thanks for having me on.
We love it when you present. You always have some really awesome stuff for us, and I'm excited. So I'm just going to sit back, grab my popcorn, and enjoy the show.
No pressure. Thank you so much. All right. So I'll get started here, if that's all right, Nathan.
Yeah, absolutely. I'll pull myself out. Let me know when you need me.
Sounds good. All right. So I'm going to be sharing my screen here, and I'm not going to have so much as an organized presentation as I've had in the past. This is just going to be a miscellaneous catch up for stuff that's laying on my desk and my workbench. But next week or two, I'm hoping to do a little bit more deep dives into the circuits I'm working with, not to make them more complicated, but to actually make them more accessible, more simple to for the regular non-engineer to enjoy high voltage plasma. So here, I'm going to finish here. See here if this is going to work. All right, almost there. Okay. Let's see. See if you guys can see a big red donut like me. All right, so I shared a little bit about this in my last presentation, but what you're seeing here is my attempt at a toroid, and I have had it 3D printed in half here. The grooves are about 1 millimeter wide, and the depth is about 1.5 centimeters. And so what I'm doing here is wrapping about 100 turns of wire per groove, and it's magnet wire, and then with the goal of having a Tesla coil, toroid shaped Tesla coil. And so this is, it's not very big. As you can see, there's the famous big lighter that I include in all of my presentations. And I don't smoke, but I have a lot of lighters around. So you can't have too many lighters. All right, so this gives you a little bit idea close up of how I'll do the windings, and then I'll drop that wire down diagonally to the next groove. I'll do some more windings, drop that wire down to the groove, and so on. So once this is filled with epoxy, then when you charge this with electricity, you have basically a whole bunch of individual coils that then combine to make a really strong electromagnetic field. And that electromagnetic field, when it collapses, it pushes out a lot of energy in the form of voltage and amps. This is even a little bit closer look. It kind of feels almost like art. It's or crocheting or knitting. Funny, a lot of people don't like coiling, but I actually find it relaxing and enjoyable. And here's a little bit closer look. So I put them in some green forms, and I filled them with evacuated epoxy. And it's a messy business when you're working with epoxy. And so this is about as much of update that I have. The goal is to then connect this up and run some current through it and see what kind of sparks we get. And then I just include this little video here. I placed these 20-pound spools of wire on a stereo turntable from the thrift store. And because it's perfectly balanced, I can pull this wire that's the size of a person's hair, and it never breaks because it just spins with you. So I thought this was a fun idea. I think I've shared this in the past, but sorry if I already did. Okay, so the next random thing that's on my desk is, I don't know if you guys do this with your hobbying, but I don't like to waste wire. So whenever I'm taking something apart or working on something and it doesn't work, I pull out the wires and I throw it in a clear bin. When I hit the thrift store, I'm always looking for clear bins. They're the best because I can just look through them and see what they are: capacitors, resistors, wire, and I don't have to think. But I found some interesting pieces of wire in my wire bin, and so I thought, you know what? This little fuzz ball looking in the middle and this little ball of thicker wire, let's see if I can turn it into some kind of Tesla coil or see what the ZVS can do with it. Don't get your hopes up, but it was an interesting experiment. So in the middle is thinner wire, of course, and the outside is thicker wire. The only thing I did is just sort of bunched it up and spread it out so they kind of had this form here. Here's a little bit further look at it. You'll notice the fuzz ball in the middle has a wire that's going out under the thicker wire. That goes to ground. And then the thicker wire goes to the ZVS. And so this is really a standard setup always with the ZVS. And what I'm trying to do here is just kind of show you that it's not this scary circuit. Once you get a good feel for it, you can just start throwing anything on the bench and see what it does. And so on the oscilloscope, this is what I got. The larger sine waves are from the thicker wire, which is called the primary or coil 1 of a Tesla coil. And then the smaller S wave there, the lower one, that one is the frequency of the fuzz ball in the middle. Now, optimally, it should the fuzz ball in the middle should start as a flat line on the left and then start wiggling larger and larger toward the right. And then that means you would be having it reach to resonance. But to pull out 2 clumps of wire and just connect them to a circuit and have an actual frequency, 338 kilohertz, 2 distinct sine waves. I mean, had I played with this longer, I could have gotten some sparks, but I have too many good stuff going on. So, but I thought I'd share this because I do this a lot. I just pull things out, hook it together, run electricity through it, and like to see how it works. And so this kind of gives you a little bit of example of how I like to play around. This is another just picture of it. It's funny because I was guessing that the frequency is going to be really high. So I put that little dinky, about the size of your pinky nail, high voltage capacitor there. Now, this is starting with the new ZVS coil that I'm writing and that I'm working on winding. So when I'm talking about the ZVS that Nathan and I are working on now, that's the new ZVS. So this is the new ZVS. And when I was winding the toroid coils, what happened was a single toroid coil was giving me a little bit of saturation. And so I decided to double them. And in double them, I was able to reduce the saturation and clean up the signal. And so this was now ready for the new ZVS. And if you look up at the top, the meter there, this is the LCR meter. It's indispensable. If you ever want to know what your coil's doing, all the coils around you are doing, you need the LCR meter. You just hit the power button and it'll auto seek. If it's a capacitor, it'll tell you what the capacitance is. If it's a resistor, and then if it's a coil. And to really get a good understanding of how induction works, the electromagnetic energy that's in a coil, if you want to determine resonant frequency real quick with coils and capacitors, this meter is a must-have. And it's last time I checked, it's like $123 on Amazon. But I think I use this thing every day in just about everything I do. It just gets you intimate with coils, and that's my favorite thing to do. So this is the new ZVS coil. You can see it has 4 MOSFETs instead of 2. And one thing I like about this new design is instead of having 4 diodes for the 4 MOSFETs and 4 Zeners for 4 MOSFETs and so on, this board is very streamlined. It just has 1 switching diode per 2 MOSFETs, and it has 1 Zener diode per 2 MOSFETs. And this really keeps these 4 MOSFETs in the correct timing. And so now if you look to the right there, the 2 big hot rod coils that I wound, The little coil next to them is the new ZVS coil size, and the the giant coils, the two giant ones, are for the new design. And so I thought I'd share that this project that I'm working on here. Now I kind of give you a little bit of video so you can kind of see. I put a little fan on there to keep things cool because I like to turn up the current. I'm in testing. One thing that's crazy. Oh, look at the Death Star. I've blown out so many pieces of epoxy and set it on fire so many times. It just looks battle hardened. So this is a really simple setup. 2 capacitors. They're just hooked up to the ZVS board, nothing fancy. And then I hook it up to power, and that's it. Here is the new ZVS, the one that Nathan and I are going to be talking about, I think, in this part of this presentation. And so to kind of give you an idea of both new ZVS boards. And by the way, please save your questions for the end. I love them. I'll be going through the chat, and hopefully I can answer them. And so one of the things you'll notice about the ZVS boards that I work on is they have this giant space in the middle. The reason for this giant space is that, so I'll be a little bit honest with you guys. I'm not really good at building things from scratch. I'm actually really better in just taking other people's good ideas and then using them for my purposes. And so pretty much everything I do is taking from somebody's idea and then putting it together. And so there is a YouTuber, his name is Schematics. If you like basic electrical engineering, has a great channel. I recommend him. He built these boards for induction heating. And so if you wanted this to be an induction heater, you would not have the modifications that I've put here. You would actually put a capacitor for each square in the middle here. You would have different MOSFETs and so on. And so what you're seeing is just I'm taking an induction heater and I'm souping it up for to throw big sparks, lots of plasma, and a Tesla coil. A little bit more close up, you'll find there's a diode kind of connected by 2 green plugs right in between the tires there on the top, the yellow tires for the drag racer. And you'll see the diode up there. So that diode burns up. And so I was tired of unsoldering it and soldering it. And so I just put a little plug-in terminal there. So when the diode fries in testing, I can just pull it out and put a new one there. And it's plug and play. And you'll also notice that the MOSFETs, they're in these green terminal blocks. They're not soldered into the board. Also, MOSFETs you'll blow when you're testing. And so it's really nice to just swap these in and out, no soldering. And it's just important for testing. Once you lock down what your board can do, you can really then just solder things to the board. Make the leads as close as possible so you don't have any little antennas that will give you noise. And it'll be a good build. But just wanted to share this tip. When you're burning up components and they're soldered, think about modularity and plug and play. Again, just kind of showing you how simple things are. Just a ZVS board, 2 capacitors, some coolant, plumbing, piping, and a sphere wrapped in coil. Another angle that you can see, and the poor sphere is suffering. I'm winding a new Death Star, so let you know that this is just going to be the tester. Now, one thing that's interesting, and I'm going to see if I can make this bigger. Here we go. I have a infrared camera, and what it does is whenever I'm trying new circuits or testing circuits, I can't really see what's going wrong right away. So what I like to do is just turn on a low voltage and let it sit for a few seconds and then take infrared pictures. And what it tells me is, okay, this wire is too thin. And that's what it's actually showing here. The wires connecting to the sphere are too small. And so they're not able to push the current. And so they're overheating to, if you look at the upper right-hand corner, to 147 degrees Fahrenheit. Please ignore the date. I keep forgetting to update the date on the infrared camera. So and I like to point out, we'll see here a little bit later, is no matter how big the arcs, the plasma that's coming out of this little coil, this little sphere, the sphere always stays cool or room temperature. It never gets warm, never heats up. That ring around it of heat is the copper pipe that's around it, the bowl-shaped copper pipe. But the sphere never gets, not even the slightest bit warm, no matter if it's 18-inch lightning bolts coming out of it at 20 amps, input from the wall socket, which blows my breakers in my house. This thing stays cool. Here's another really cool infrared picture from the top. You can see that the copper pipe gets a little warm as it gets to the sphere, but again, the sphere almost is like a black hole because it just doesn't show up on any infrared. So I'm using the hot rod ZVS board, and this is what's called a quasi-continuous wave. I turn on the sound, but it's a bit tricky, and I kind of want to keep this presentation flowing. But what you're seeing here is I'm turning up the DC voltage. The DC voltage gives this really fluffy, large outbreak of plasma. But see how it goes short, and then it comes up, and then it goes short, and then it comes up, and so on. What it's doing is, if you can think about a car, a 4 piston car. And if the timing is right, the pistons are going to fire just like you want them to. But if one of the pistons is not firing correctly, then you're going to start seeing the car lose power. You're going to start seeing the engine maybe vibrate, and you're going to see all these symptoms. And that's kind of what's happening here. I have 4 MOSFETs. They have to be perfectly hitting on time. And as I increase the voltage, I'm missing something in the circuit that I'm going to figure out. But what it does is it stalls. And so when it stalls, I then turn the voltage back down again. It's kind of like turning the car off and then turning the car back on. And all of a sudden, the timing's working for a little bit longer. That's what you were seeing here. And it's an interesting phenomenon. And the sound of this is just a gentle hush, like a shh sound. And again, I'll learn how to do sound in these presentations one of these days. So, and this next, there we go. So when I'm tuning things, I've shared this before, but this is a really good example. This is why the poor little sphere coil looks so terrible, is it's because the plasma is coming out of the epoxy, and it's burning the epoxy. And then it's, so yeah, you can see, I haven't put it in this clip, but I've had coils catch on fire. So I have a fire extinguisher right next to my experiments. Also just worth mentioning, and I'll put it in a video next time on how to use it, but I have an ozone meter in the Chicago area where I live. I usually have the windows open and a fan, so it's no big deal. But in the winter, I got to close things up. And so rule of thumb is if I slightly smell ozone, it's not too bad. If it smells a little bit stronger, then you'll want to get some ventilation, because what it'll do is it'll irritate your lungs, your throat. It'll basically give you kind of a raspy, raw throat. And there's some studies that it has some long-term damage, so you just don't want to do that. On the flip side, a little bit of ozone is good because it actually kills fungus and bacteria in the air. So thought I would share that. Okay, so now I'm using the hot rod for the sphere. And you'll notice some differences here where the tendrils that's coming off, if you will, are thicker, they're brighter. One of the things I want to mention is, oh boy, wait, is this oh no, this is the 2 MOSFET. Oh, sorry about that. Let me see here for a second here, what's going on. Okay, so what I'm doing here is I'm putting in AC from the variac. And as I increase the AC from the variac, Oh, it is the hot rod. Okay, I'm right. What you'll notice is the plasma discharges are a lot thicker. They're a lot brighter. You can see that the swirls are more prominent, and you can't hear it here in the video, but when I turned it on, it starts to ramp up with noise. So right now here it's super loud, and it's probably 20 volts, then 30 volts, then 40 volts, then 50 volts, then 60. I wish you could see this. I'll show this on a meter next time and not have to say it like this. It's a little silly. And so this is about in that 60 volt range. And now as I bring it into that 70 volts, what you're going to see here is you're going to start seeing this little skinnier tendrils, little lightning coming behind the thicker ones. And so what that's happening is as something mechanical is oscillating, it's given a really hard, loud noise right now. And it's kind of hard to see here. Let's see if I can pause it and catch it here so we can see it. Let's see here. No. There we go. So you see these thin guys right here, if you can follow my arrow. And then here's the thicker ones, that what I call the tendrils, the twirls or the swirls. So the new ZVS gives a lot thicker plasma. And actually the plasma is more spherical, you'll find out as well, than it is with the other 2 MOSFET ZVS. But these will start appearing behind it. And that's that sort of jump from 60 volts to 72 volts AC. And it's really loud. And so I kind of wanted to share that because as I begin to do little tweaks on the ZVS board, what actually ends up happening is as I get to 60 volts and 70 volts AC, then all of a sudden it becomes silent. And it becomes silent all the way up to 100 volts. And it's a little, it's very cool, but a little eerie because it actually should be making a whole lot more noise. And the reason for that is there's no mechanical, no physical device that's oscillating at its resonant frequency, making all these weird noises. I think this is just another display, AC, going through the sphere. And you can see let's see here if I can catch it again. So you can see the thin tendrils behind, and they're a little brighter if you can catch them. You can watch them, see how they're thinner behind, and then you have the thicker ones closer to you. And that's that jump from 60 to 70 volts AC. And it's really kicks in loud when you see those. Actually, I just threw my 20 amp breaker in my house, show you the kind of power that I'm using. Now, one of the things I did is I like to do with my coils is to connect them to different things, see how they can interact with different things. In this video, we have the sphere coil right here, and it's putting out a little output. This is 6 volts AC. And we're seeing here probably about 50,000 volts. And this is just because it's a well-tuned system. The closer you get to the resonant frequency of something, the way less power you have to put into it to get these beautiful plasma discharges. But in this video, what you're seeing is over here on the right, there's a copper needle, and it's pushing out the plasma out into the surrounding air. But what you're seeing here on the left is it's a copper tubing that I've connected directly to ground. And what's interesting about this, I live in a 125-year-old house, so it has a really high water table. In fact, if you dig like a 2-foot hole in my yard, you'll start hitting water. In my basement, I actually have a water well in my basement. And so it was very big in the old days to make sure that your house was super well grounded. And so there's these huge copper pipes being driven into the ground. And so this house is well grounded, and these copper pipes are hitting right into the water table easily. And so what happens is, even though this is just a little 6 volts AC here, you can just see the outpouring of current coming from the ground. And you'll notice too, it's hitting the base here. It's hitting the sphere, and then the sphere is then pushing it out the top here. So pretty incredible. a nice visual to see how the Earth really has an abundance of electrons if you're willing to pump it out, if you will. And it was Nathan that made the good analogy of this. This is just a little 6-volt pump here, and now it's pumping plasma electrons from the Earth, real Earth too. Not like when you look at a schematic and it says ground and it's not. It's not Earth ground. Okay, now we're going to end up in just real random stuff. What kind of gloves do I use when I'm working with plasma? I wish people would have told me this before. Now, I use these gloves because you can still use your phone or your iPad, and yet it's a nice rubber seal for if you're doing light soldering and stuff. It's cut proof, so when you're doing a lot of wire work and using the X-Acto blade and stuff, these are not cut proof, cut resistant. And they're you're not going to get shocked in them with the outlet, the wall outlet, not unless you have a little crack in them or something. But I live by these gloves. And then last but not least, at Amazon, they're super cheap. So I thought I'd share that. I'm going to kind of share some things that are random like this that I wish I knew before I started the hobby a little over a year ago. My favorite meter, the LCR. You can rule the electrical engineering world with an LCR meter. Can't get enough of this guy. Here it's telling me my capacitance at 1 kilohertz. So I can change the frequency to see how my capacitors react. I could hook it up to a coil like I showed you earlier. I can change frequencies to show you, oh, that frequency really pushes out a lot of power. So, and there's no thinking on this. You just push the button, and if you'll see the LCR auto button under the power, if it starts turning out, you can't figure it out, just hit that button auto and it'll figure it out for you. So really cool. I recommend it to everyone who's interested in plasma and coiling. So I was looking for a high voltage probe. Wanted in the 20 to 30,000 volt range, and they were running hundreds of dollars. So I picked up some resistors. These are 50 mega ohm, 100 mega ohm resistors. They're 8,000 kilovolts. I'm sorry, 8 kilovolts rating. So if you connect them like this, you're doubling and tripling, quadrupling that rating. And I round them in a sort of helical pattern, kind of like a DNA pattern. And then I placed them in epoxy mold and then came out. And so now I have a 30,000 volt probe, and it cost me just under $8, and it works really well. So yes, this part here is the easy part. There's a little bit of calculations you have to do to figure out how you're going to use it for your meters. And so if you guys are interested in that, totally reach out to me and I'll be glad to give you it's just one math formula, and tell you where to order these resistors, and you can start building your own probes. And what I'm going to be planning to in the future is I'm going to be taking this probe into the heart of all the high voltage areas of my Tesla coils and let you get some insight on what's going on. And there you go. It's 487 million ohms, so half a giga ohms. When you have that many ohms, it's so crazy. If you have a temperature drop in your house by like 10 degrees, that 487 million ohms will change. It'll be like 479 mega ohms, and it's fine. It's within tolerance. But when you have this many ohms, the outside affects the ohmic readings. So let's see here. I'm trying to remember this slide here. So I'm connecting things random on my bench, and I just look at the waveforms, and I'm looking for a certain pattern, and I'll show you that pattern in a little bit. But this is not the pattern I want. But it's a lot of fun to see what I'm playing with. Oh, I'm sorry. No, I'm tuning this. Sorry, forgive me. As you can see, it's coming out of the plasma. So I'm not getting the waveform on little sphere here. And I need to get that right waveform. And so how I tune to get to the right waveform is I changed the capacitance. So you'll notice that there's some capacitors there connected to the ZVS here in a minute. If I don't have the right capacitance, it's not going to hit the right frequencies. If I don't get the right frequencies, it's going to do stuff like this, which you're going to see. What it does is it becomes an unbalanced system. And so if you don't tune it right, see the lightning shooting off toward the sphere, toward the epoxy? That is not tuned. It's not balanced. When it's balanced, all of the plasma comes out the tip. None of it will go out the side of the epoxy. This also kind of shows you that the voltage is so high that even just the slightest mistake in distance or geometry, then you have plasma coming out all out of every side of and destroys things. What you're seeing here when it's destroying things is here when it turns white, that's literally melting the epoxy. So just thought I'd share that. Another meter that I use sometimes every day is this little tiny, it's a 10-in-1. It's a multimeter, O-scope, but I don't use it for any of those purposes. I use it because it's a transistor or MOSFET tester. So if you're ever frustrated and you don't know if your transistor is working or not, or your MOSFET, and yeah, you can check your MOSFET with a multimeter, but you got to kind of do a little bit of calculations. This you don't. You just push the button and boom, it'll tell you if your MOSFET's still working or not. So I recommend this. Again, it's cheap. You'll find that my test equipment is on the inexpensive side, but it's on the quality side. I have a certain level of quality that I need. So as cheap as I can get, but quality. Let's see here. So I'm being a little cheesy here, but I'm kind of nosy. I kind of like to see what people's workshops look like and labs. And so I thought there might be some nerds like me. So what I'm doing here is just going to do a 360 here in my lab, and you can kind of get a look of what kind of Frankensteins I'm building and how I use things. So this is my lab. I started building it about a little over a year ago. So I'm very new to the craft, new to the hobby. Yeah, don't look at my messy shelves, but in those shelves are probably 100 projects. There's my 6-foot whiteboard in the back there. I fill that up all the time. Love it, brainstorming. And so, yeah, sit stand desk right there for soldering. iPad, because I always need to be watching Old Man Builds or The Benefactor. So you know how that goes. And so here we go. That's my lab. So I took a piece of pipe and I wrapped it in with some junky wire. There you go. And I just connected it to some capacitors. I found this coil that I wound of 200 turns of wire, and the wire's thinner than a hair, so it was pretty torturous to wind. And I connected it to the ZVS. And so what's funny is that little tiny hair wire, which is basically, again, I'm making a Tesla coil. It's putting out so much power that it powers this light bulb here, this little hairline. And what you're seeing here is just, again, the output of a Tesla coil, but it's not conventional because I put the primary coil in the middle, and the secondary coil was on the outside. And you can do that. You can have fun with putting in the coils here. I'm going to show this one more time. So I put the primary coil, which is always supposed to be on the outside if you look at all Tesla coils, or most, but on the inside, I mean, on the outside is then the secondary coil. So it works. It's fascinating. Not tuned, pretty ridiculous as far as output, but fun. Now here, I'm just kind of trying to give you a visual display of when you turn on your ZVS and when you need to turn it off quickly. Okay. So when you turn on your ZVS, It shouldn't drop to 7 volts, 42 volts. It should not drop to 7 volts. It should be 42 volts all the time. Okay. So it should always read 42 volts when you turn it on. And then it should just read a little bit of amperage, maybe like 0.9 amps or 0.5 amps. That's what it should read at 42 volts, or maybe 1 amp if it's a really big coil. But it should never be doing this. Okay. It should never be going to 24 amps. Yeah, you're going to fry something. You're going to burn something up. You're going to catch fire. So that's really a really good indicator on saying, hey, nothing's oscillating. My ZVS is not liking me. I got to figure out, maybe my alligator clips came off, or I smoked a diode or a MOSFET. And it's just literally one of either that one diode I showed you or one of your MOSFETs. But this should never be the case. And I kind of wanted to reemphasize this point because people are building ZVS boards and they're not really understanding them. And I a little blood and tears. And I learned this little tip here is that if you turn on the power and your voltage goes down and your current goes crazy, turn it off and figure out what's going on. All right. Let's see what I'm doing here. It's nice when I take a break here and get some water. Oh, okay. So remember I put the, there we go. So that thinner than a piece of hair wire, it's only like 200 turns. I put a goofy piece of plumbing pipe in the middle with some old wire, and it's lighting up the fluorescent bulb. It's got this really interesting wave pattern. The giant peaks are the coil inside. The little peaks are the coil on the outside. It's not your perfect waveform, but you saw it light up that fluorescent light. And so you're getting some really serious voltage already. Had I spent a little time tweaking the capacitors, we would see that little hair wire pushing out some plasma. But again, just having a little fun. I'm going to throw a little coil in there, wrap it with some hair. Boom. There you go. Look at that. It's pretty crazy. It doesn't seem right that so much electricity can be coming up through such a small wire and so few turns. That's the beauty of the ZVS. That's the beauty of resonant frequency. That's the brilliance of Tesla. He is the man. Okay, I'm showing you my little tester meter real quick. Oh, look, my MOSFET works. If you don't get this, then your MOSFET's broke. So I'm going to show you here real quick how to test the diode. A good diode has a voltage going one way on your meter. So it's 0.3 volts. And then if you switch the diode, I'm going to switch it around. And then here, okay, now it needs to read an open. And that's when you know your diode's working. It's like a check valve. It only lets electricity go one way. And so I thought I'd include this. These are nice little tips I wish I had when I started, but that's how you test the diode. So how do I test then if the diode's faulty? Well, it'll be a direct short or it'll be a direct open, both ways. It'll be open both ways, or like a shorted, like a piece of wire both ways. But it won't give you a little voltage and then an open. That's a good working diode. I'm kind of showing off how things are modular. So I buy these little terminals. Here I replaced that diode that burned up. And I'm just going to snap it in here. And I'm going to put these guys in their little terminals. And guess what? My board's working again. So I don't feel intimidated by blowing circuit components up. And I use cheap MOSFETs. When I say cheap, I mean Mauser, inexpensive. So they're quality, but I don't pay more than about 80 cents each. I know people have some really nice MOSFETs and I'm envious of them, but I fry them when I'm learning and testing. So I'll stay with the cheapies until I get better at this. So sometimes I just like to throw my coil on its side and see if I can get plasma out of both ends, and I can. That's pretty cool. And what's cool about this again is this is about 7 volts, 6, 7 volts. Shows you how the power of resonance. Pretty amazing. There's about 2-inch gap here. Now my coil is 6 inches wide. It has 5,000 turns of wire, and I'm doing the same thing. Connect a capacitor up here, just one capacitor. I'll coil some pipe around my inner coil that's covered in epoxy, and I just connected it to 2 copper pipes. And then what you have is you have this really cool plasma. I like to kind of see what shapes I can get with different geometric connection points and so on. So I'll be sharing more about that later, but this is cool stuff. Here's another one. I just thought I'd take these paper towel rollers that I got at the thrift store. And oh, this is 10 volts. So my Variac shows a little high, so it's like 3 or 4 volts too high. So that's about against 7 volts, probably 6 or 7 volts. Okay, this is going to get interesting. So this right here is my Gauss or Tesla meter. And so what a Gauss or Tesla meter measures is the magnetic lines of flux, or the magnetism, or more correctly, the electromagnetism the sphere is creating. And so you saw me start from the top here, and you'll see this little transistor here. That's it's a Hall effect sensor that tells you. I think it works like a Hall effect sensor, and it tells me what the magnetism is on the top and what the magnetism here is at the equator. Also, when I powered it up, because it has to be powered up for you to test it, because otherwise it doesn't have its magnetic field created by the electricity. I don't know how many times an arc came out and touched my little transistor here, and I thought, oh man, I fried my meter. And a Gauss Tesla meter, a good one. They're not cheap, but no, I didn't. This little probe here is pretty tough. I had some serious 2,000-3,000 volts running through it a few times, and it's still working. So I don't recommend it though. All right, so from my measurements and my research, this is what was going on with the sphere. So I measured 334 Gauss on the north part of the sphere, and I measured about 329 Gauss from the southern sphere of the sphere, because the sphere is acting like a magnet here, but it's acting like a very specific magnet. It's sort of acting like how the Earth's magnetic field works. Now notice here at the equator, the Gauss was 1/10. Oh my goodness, even less than 1/10. Very much lower at the equator than it was here at the top or at the bottom. Now I'm not sure if you remember, but when I would place objects next to the sphere, it would not interact with it. It would ignore it. And when I placed even my cell phone around it, it just didn't interact. Well, the reason is because at the equator, it has such a low electromagnetic field, and it really concentrates the electromagnetic field at the poles, so the South Pole and the North Pole. And so this really fascinates me, because this geometry really provides a way to really focus focal points of dense electromagnetic fields that result in those big plasma discharges. And so this is good to know. On the outside, this is called a dipole. So outside the sphere is a dipole. If you're not familiar with the dipole, all that means is di is 2, pole is for what you're seeing here, North Pole, and down here, the South Pole. So this has 2 poles, so it's called a dipole. It has uneven magnetic lines of flux. We talked about that. That's crazy cool. I really think there's some things that we can do with this concept here, having a Tesla coil with like null points. So that's interesting. And the last thing is, you would think that there'd be some curvature in the magnetic lines of flux inside the sphere. And that's just not the case. The electromagnetic lines run straight inside the sphere. So that's really a fascinating idea as well. I'm working on printing and winding a transparent sphere because, and this was Nathan's good idea, and to see if we can kind of peer into what the electromagnetism is doing with these super straight magnetic lines of flux. And so I feel like this is a breakthrough. I feel like this is exciting. And I think there's more to come with this. And I hope I get some questions on this at the end. And thank you for you guys' patience. This is going a bit long, but I feel like this is some helpful stuff for when you're using plasma, and so I'll get through the rest of it here pretty quick. So when plasma discharges, it leaves a I don't even know how to say it now. It leaves a kind of fractal structure. And so on the left here, you'll see a charcoal kind of line. It's really hard to see. I'll throw it on my microscope here pretty quick, and it might be a little clearer. But what's interesting about these discharge points, these plasma discharge points, is that when the electrons leave the sphere and they shoot out of the this acrylic, it leaves no mark on the inside. It only leaves a mark on the outside. And so what you're seeing here is this is a rough, melted surface, this charred surface here in each of these discharge points. But if you reach your hand in there, it's perfectly smooth on the inside. And so that's really interesting. How are the electrons going in, creating all kinds of heat, but the heat only goes to the outside? There's no heat on the inside. So thought I'd share that. Pretty interesting. Here's a little close up. And when I talk about fractals, it just sort of starts to look like what you see here with mountain. At 50,000 feet, you're seeing a mountain ridge, and you're seeing all the rivers and islands and stuff. Sorry, one second. Sorry about that. My puppy was getting through the door there. And so this is probably not too interesting yet, but I think it will get interesting as we talk a little bit more about it. Look at how clean my sphere is. This is when it was before I beat it up. But you can see that it's that acrylic piping is what's holding the sphere up. That's where it's located. That's where it was pushing out the lightning bolts out of. Now, when I look at the infrared of that acrylic cylinder that I just showed you, the discharge points, the fractal discharge points, excuse me, they show up as hot. Now, this was driving me crazy because when I was putting my hand here and touching it, it was not hot. In fact, the circuit was turned off for some time. But when I look at it in the infrared, let's see here if I can make it bigger, it was showing up as hot. So these fractals seem to bend light in such a way that it gives an actual heat signature. Thought that was pretty interesting. I thought I made some big breakthrough, so I was going to maybe call the Department of Defense and make some kind of fractal uniform so infrared seeking drones won't get you. But that's already been done. So nothing's new under the sun, unfortunately. Though I think we're making some great discoveries in our fringe science groups. And so here's a few more close-ups. And so it's a little bit hard to see here because my I don't have a good high definition microscope, but you can see these little. These actually look better in person. But they're little. They basically look like edges of a Mandelbrot set or fractals. You can kind of see it again here with my microscope. These little fractal type images. And I wish I could have gotten some more light in the darker parts because there's some more interesting shapes. This was another very interesting shape from that charred discharge from the plasma. This is really fascinating to me. I just ran a a red laser printer through the fractals, and it looks like lava flow. It looks like corpuscles at the bottom of a volcano, and I thought that was interesting. And of course, these are just created by plasma discharge, so there's no on-purpose manipulation of these designs here. This is really being a laser being put through it is forming all of these different structures. It looks like they're structures, but they're really how the light is being bent. So I thought I would share that. Pretty fascinating. Another fascinating thing here, and it's really hard to see here, but when I point the laser pointer, and I should have a better one. This is a real cheapie. But when I try to shine it through the fractal discharge points, I'm getting a lot of the different designs that I had noticed in Victor's presentation. So you're seeing some geometries here that are even similar to some of our coils. Oh boy, Nathan, when he did his presentation on some of the sacred geometry, when you're here looking at it, and I'll get a better laser and see if I can get some better quality recording of it. But man, oh man, I'm looking at all of these different types of coils. It's so fascinating. The chalice coil, the star coil, almost a rodent in there. It's just super cool. Thought I'd share it again. You never really knew how much fun stuff is in a charred piece of plastic. So I built a jig, and I wanted to be able to just wire different types of designs. I think I'm trying to do a star here. And so this is a lot of the things I like to do is just 3D print some designs, wrap them with wire, and throw them on the ZBS. This is kind of one of my harebrained experiments. I'm sweeping a frequency, and what I'm doing is I'm taking a ultrasonic transducer, and I'm blasting out ultrasound, right into the plasma of my sphere. So you can see that black cylinder there is an ultrasonic, I think it's called an ultrasonic horn. It's excruciatingly loud. And did I see anything interesting? No, but it was interesting to do. I think I'm going to start working on if I can get the mechanical frequencies of stuff on my Tesla coils, and then tune these transducers to the mechanical frequencies and see if I can get them at the same resonant frequency as the plasma coming out of the discharge end here. I think that would be something to watch. And oh boy, that's it. Hey, thank you guys so much for paying attention. Thank you for being interested in a nerd in Chicago and his presentation. Nathan, you still there?
I'm here, Shawn. That was totally awesome. Let me bring everybody back in.
Okay.
And Gerald
Yeah, that was
disappeared
really
again.
awesome.
Yeah. Hey, everybody, give him a round of applause, will you? That's for you,
Thank
Shawn.
you so much.
You deserve it, brother. That was
I
awesome.
appreciate that.
Yes. Yeah, there were so many key points in that presentation where I'm like, wow, that's cool.
Thanks, guys. That means a lot. I appreciate it.
Yeah, I like how you thought of shining the laser through the damage, the acrylic damage, to see the pattern on the wall. That was brilliant. Absolutely brilliant.
Thank you so much. I appreciate it. I was kind of a little bit hesitant to let you peer into my lab and in my insanity. But you guys have been so wonderful, and this is really just a place for ideas to flourish. And I just feel the love in the chat. This has just been awesome, guys. And so I appreciate that. I appreciate all the kind remarks.
Yeah, of course. I mean, you've seen my mini lab. It's like a little table, a little fold-up table.
I
It was
love your
embarrassing
lab
for me
coat.
to try to, go live at first, but at the end of the day, the science is more important, and we're here for the science, and it's fun science.
It is. It is, and it's fun to Google it and not find it anywhere. So you kind of feel confident that, hey, we're getting into undiscovered country, and that's feels fun.
That is the most exciting, the uncharted territory part. That to me is like we're discovering new things that people haven't, paid attention to or seen before.
Right. Exactly.
Yeah,
I mean,
sorry, go ahead.
no.
I was going to say, when you show the magnetic fields of that sphere, that's like mind blowing right there.
Yeah.
It's weird because we saw the phenomenon, and now it's to explain the phenomenon. You just wouldn't think that there would be points of very low energy, and then it doubled and focused from just it's just a ball. I mean, okay, it's just a ball. Thanks, guys, in the chat. I appreciate that. I appreciate it a lot. I kind of just thought you wouldn't really see much of a change, and no, the change is drastic. Um, and I told you, I moved a ground wire to the hemisphere. Didn't want it. It's so crazy. And if you, just so you know, if you guys don't do Tesla coils, bring a ground wire in anywhere near a Tesla coil, and they love the ground wire. Just so you know.
Because
Right,
they're
Nathan?
a pump.
Yeah. Yes.
That's right. Love that thing, man. That is so unique, Shawn. You're the only one. You're the only one that does that. Okay.
Thank you. Thank you so much. Appreciate it. So any questions in the chat? I for some reason I'm not. Oh, here we go.
Sorry about that, Shawn. I held some of them back because you're presenting. I didn't want to distract you. So let me go back up.
Sure.
I had a question, but I forgot to write it down. So, I'll think of it eventually. It'll come back to me.
No worries. No worries at all. I'm just happy you guys made it through. It's not easy to sit through an hour presentation.
No. With your stuff, we're all good. Always. Don't ever worry about that.
Oh yeah, it's
Thank
fun.
you.
Like it's like a lot of people like wouldn't be able to, I guess, but I think it's fun. I eat this stuff up.
No, awesome. I eat it up. It's if I'm not smiling watching your guys' YouTube channels, I'm smiling in the lab.
My girlfriend probably thinks I'm a big nerd, but it is what it is.
I love your lab coat and hard hat, dude. I have to get it.
Oh, yeah, that's
absolutely
the
love
goal.
it.
I want everybody on the team to get a lab coat, so we all like have like a team, kind of like a uniform, almost.
Yes. I have to. My wife rolls her eyes, but
Hey, I've gotten a couple of negative comments on it, but I don't care. I think it's fun. And it's important when you're dealing with when you're also dealing with fluids and stuff. If you get something on you, you need to be able to see it. You don't want to be wearing your civvies.
yeah. Did you say skivvies?
Civvies.
Oh.
Civilian clothes, not your britches.
Well, that too. You don't want to be Doc Brown in your boxers and a lab coat over. Marty!
Nice.
Oh my.
That's so funny. So I'm going through some of the cool comments here. Wizard of Woodstock set current to a constant on power supply. I know you know that. Yeah, it just depends on what I'm doing. Since I know if the voltage drops, the current's going to go crazy. It's kind of good for me to see it. If I set the current to only be like, let's say 1 amp or 2 amps, I won't really see how bad the damage is. So sometimes I just like that huge drop of current. So I set it on max. But good point to make. Oh, thank you, Crypto. I appreciate it. I'm so happy that you're part of this journey with me and building and designing these experiments. So I appreciate that. Oh yeah, 24 amps is huge. And I'm going to connect it to my 18 amp power supply, just so you know, because it's not huge enough for me. I need 50. So that's my goal. Because I want 50 because the new new ZVS can handle it. So yeah, the primary in the center, it's kind of a crazy idea. Let's see. And I get these spur of the moment experiments, and I'm like a cat with a laser pointer, so I don't get a lot of what I want to get done, but it's just more play.
No,
0.5.
hold on, Shawn. No. Don't just gloss over that. Nobody puts a primary in the center. They always put them on the outside.
That's true.
That's
true.
that's something big, man, just to get it to oscillate properly when you change the configuration. Well, I guess when you're making spheres out of stuff and donuts, it doesn't really matter when you do that, but it's important for the Tesla coil community to see it.
That makes sense. Yeah, I'll do a nice one then, where it completely runs the primary in the middle, and because I appreciate that feedback. I'm taking things for granted sometimes. Mike says that reverse bias drop is 0.5 volts. Yeah, it depends on the diode. It's usually between 0.7 volts. The reason why mine was lower, 0.3 volts, is because it's a Schottky diode. But good catch there, Mike Thank you for the input. Let's see. Cap increases power factor, right, Shawn? Well, from Wizard of Woodstock. So something weird about capacitors. If you connect, let's say, 10 capacitors in a certain combination and get 100 nanofarads, and then you go in your bin and grab out one single capacitor and it has 100 nanofarads, that's kind of why capacitors are hard to get your brain around. So if I'm using the one capacitor, then I'm going to have a lot less current because you can store less joules of power in it. But if I have the, let's say, 10 capacitors configured series and parallel to equal 100 nanofarads, I'll handle a whole bunch more not coulombs, but joules of energy, and you'll get a lot more power through it. So I hope that responds to your comment. Let's see, smash that like button every time. Oh, thank you. That's the one. Sorry. That's the one I'm ordering, little scope. I'm not sure what scope you're talking about.
I think he was talking about the little tester that you use for your MOSFETs.
Oh, yes. Yes, the little O scope. Yeah, you can test your transistors with a multimeter, but I'm dyslexic, so I'll get things backward all the time. So I like automated, and I think that thing costs like $30, $40. So yeah, it's the best transistor tester, and it'll test other things, but I only use it for transistors. Let's see. Jack Pollock painted the Death Star coil. Yeah, it's got chunks blown out of it. I use hot glue.
Yeah.
I use hot glue to fill it in because it's all over the place.
Did you notice
Yeah,
in
it
your
looks like
testing
it's
that it was glowing?
No, I didn't. I got to write that down. It glows?
So all of your plasma discharge is coming onto that filler that you put in there. So at the top of your round Tesla coil, it starts to turn like a purple color, which it could just be the brightness of the sparks coming out and reflecting, or it could be that you're getting ions there. And I wouldn't know unless I was in the room with you, but
Yeah.
it definitely glows purple.
Yeah, that's cool.
I'm going to look for it now. Thanks.
Yeah, I didn't notice that. Yeah, like you said, it's something that you have to see with your own eyes, huh?
Well, just to see if it's volts or if it's just like something heating up the glue to make it get that color, like a 3D printed glow print would show the color in it.
Yeah. No, that's a good check or good idea. I'm gonna definitely look for that. Oh, thank you, crypto. Take my time. I know I gotta take my time. Appreciate that. I'm a spaz. I don't know if you guys didn't notice that yet. So a good spaz, I guess. Thank you, Wizard of Woodstock. I appreciate it. Thank you, Ben. I love all the love. Eric Dollard would be proud of me. Oh my goodness, that's high praise. I don't even know what to say to that. I'm blushing. Thank you. Maybe electric geology is not so far-fetched. You know, if you're referring to rocks and stuff, yeah. Oh yeah. I love connecting geometry to electricity. It's awesome.
Well, I've always said that heavy metal and voltage go good together.
Nice.
Nice. My wife likes heavy metal. It's cracks me up. That's cool.
Oh, trust me. When I get this rodent coal running, we're playing Thunderstruck right through it the first time.
Nice.
Yeah, that's gonna be awesome.
Yeah. So did you say external carbonization? I did. When the plasma goes through acrylic or any insulator that's clear, well, any insulator that I've tested, it's always smooth at the entry point, and you see the damage and the char on the outside. I don't know why that's so. I'd have to look it up because it kind of doesn't make sense. If it's hot enough to melt and char, why isn't it melting and charring on the side that the electrons enter? So that's fascinating to me. Probably have an answer in our next presentation. And just to let the guys know, I've asked Nathan if I can present once a week on Wednesdays. And so just to guys that let you know, I have a whole bunch of stuff to share. This is the tip of the iceberg, but as long as you guys will have me, I'm glad to share.
Oh, every Wednesday, Shawn. Every Wednesday. Every day you can come get up and do this show. Perfect.
Thank you. I appreciate that so much. Awesome. Looks like art. Thank you. Yeah, I love the aesthetic qualities to plasma and electricity and magnetism, and I just think it's cool.
So Shawn, you were saying you were thinking why it was smooth on one end and not on the other. I don't know if this helps, but if you're getting negative electricity, which you probably are, it's going to be cold, right? Or colder than normal electricity. And it's just potential until it reaches the conductor. Is acrylic a semiconductor or a conductor?
It's a insulator. It's not supposed to
It's an
let any electricity.
So it's
through
not
it.
supposed to. Oh, that makes it a little more difficult to wrap my brain around then. Because if it was a conductor, you could say, it was just potential until it hit the conductor,
Right. Yeah. When you play with plasma, it goes where it wants to. So it'll go through plastic, an inch thick of epoxy. Epoxy is supposed to be the most resistant insulator.
Yeah.
I've had to go through 2 layers of acrylic, an inch of epoxy, and through my 600-volt electric gloves, and it gave me a good zap. And I just thought, oh my goodness. And that's the whole thing about an unbalanced system, is that it's plasma becomes really unwieldy, and it's destructive. So when you see something just throwing out lightning bolts and it looks all pretty, there's a lot of balance and tuning in that. And it's more of a feel thing. I know I shared with you, I'm more of an intuition designer, developer, builder. And
Yeah, we don't.
Mhm.
I was gonna say we don't see it, but like if the camera pans in some of your videos, I'm sure you're behind a Faraday cage of some sort.
I'll tell you what I do is I wear a welding full face shield, gloves.
Oh, okay, that works.
And I have a fire extinguisher. And what else do I do? I mean, I have all of my stuff on surge protectors, the real good ones. So if I get 15 amps going through me, it'll only go through 1 second. So I have layers of safety, layers and layers of safety.
That's good. Yeah, no,
Yeah.
you definitely like that's something I do. I keep a fire extinguisher right next to my table when I'm, working. You have to. You don't know what's gonna happen.
Yeah, it's smart. I didn't know that when you overload semiconductors like transistors or diodes, that they explode. I mean, I've seen capacitors explode, but man,
Yeah,
and so that's the face shield, is because I don't want a piece of PNP junction from a diode in my eyeball.
exactly. Yeah, because I've seen capacitors pop, the little small ones, but I got the big ones now, and I'm like, well, what the f happens if the big one pops? I need to, I need to have some kind of protection.
Exactly.
Well,
The
they're like little
Mhm.
rockets, so they use up all the liquid inside, and it heats real fast, and then it
Huh.
explodes out.
And
Yeah.
it shoots itself up. Oh boy.
Not that I
Ye-
do that on purpose or anything, but it
Yeah.
happens.
The person who lives upstairs isn't going to be too happy if that happens.
Right. Right. Yeah. It's what is it? Try a ceramic capacitor on your Tesla coil. Oh no. I mean, get behind something. Yeah, they blow.
Oh,
And
you get
it's
some
funny.
great sparks out of those.
What's that?
You get great sparks out of those.
Yeah, for the voltage doublers or the Cockcroft Walton multiplier, the high voltage ceramic caps are great, but that's because there's no frequency. It's frequency that causes those high voltage caps to blow up.
Hmm.
And I know from experience, unfortunately. All right. Wow, just a lot of nice words. Thank you guys. Appreciate it. And I'm not sure what tickle me Elmo means, but thank you. Let's see here.
Oh, that
So,
just
Mr.
sounded
Lanius,
wrong.
sorry about
We
that.
have a tickle me Elmo.
Yeah, it sounded all wrong. That didn't sound right at all.
Yeah, Wizard of. Oh boy, Ben. He gets goofy when he puts on the hard hat. I love it.
Oh man,
So,
so great.
Mr. Lanius, I listened to your guys' live stream, Nathan, on Sunday. Wow, what a reservoir of information. I mean, awesome stuff. And yeah, when he mentioned my name, I was so touched. So just the love actually on that Sunday. I appreciate you guys so much. I mean, it meant a lot. But yeah, Mr. Lanius has mentioned maybe I could assist him in testing his electrodes. And not sure if you guys have seen his electrodes, but wow, oh my goodness. It'll be like candy in a kid's store. So, or a kid
What is
like
an electric?
in a candy store.
What is it? An electrics?
So, to put it in simple terms, you know how a permanent magnet, it
Mhm.
always has magnetism. You can has a north pole, south pole, and it's permanent. You don't have to run
Mhm.
electricity through it to get it to magnetize. It's just in and of itself has that magnetic field around it at all times.
Right.
Well, an electrode is like the opposite of that. Instead of having a magnetic field around it, it has a electric charge field, and it gets that electric charge field because it basically starts out as a capacitor. So you have a
Mhm.
copper plate on one side, an insulator in the middle, and a copper plate on the other side. But what an
Mhm.
electret is that it runs super crazy high voltage, and they heat up that insulator. And what happens is that the electron orbits get distorted inside. They turn them like ovals, and all the positive side of the atom is on one side, all the negative of the atom is on the other side, and it's just
Oh,
like
it's
a
a charge
charged
separation.
capacitor. Yeah, and then when it cools, it stays charged. It stays with that field like a magnet, except for a capacitive charge field around it. I'm no expert on it, so Mr. Lanius is, and so that's about as far as I know about it.
So it has to have an electric current going through it to produce the magnetic field.
No. So a capacitor, if you held a 9-volt battery to a capacitor and then pull the battery away, that capacitor will hold 9 volts. Okay. Um, and it will basically have a electric charge. Well, what happens is that no capacitors are perfect. So over time, that 9 volts will go to 8 volts and 7 volts, and it'll sort of fade
Oh.
away. What an electret is that they charge that capacitor, but not with a 9-volt battery, with like a 9 million volt battery.
Mhm.
And then they let the dielectric that's between the plates heat up, then cool. And then they can take off the 9 million volt battery, and it's still stuck in that 9 million volt state
Oh, wow.
with the electric field. The 9 million volts aren't on the plates, but the
Right.
field is like a charge field. And so if you recall how the sphere's magnetic field lines bent into each other, if you notice that, but an electric charge field does not do that. Electric charge field sticks out in all directions straight.
Hmm.
And it goes straight
cool.
forever, kind of like a sea urchin. And the only time you'll see the charge lines bend is if you bring another charge next to it. And then what will happen is then they'll start to bend like magnetic waves do. But it's really fascinating. It's in the electrical sense, it's like a permanent magnet, but it has nothing to do with magnetism.
So, when capacitors get run down, like the polarized ones with the plates, is that always like, or sometimes like a process like batteries where they sulfonate, or is that something different when they break down?
It's a good question. So electrolytic capacitors are used because they're cheap. And that's kind of the big reason why.
Right.
And they do have an electrolyte type substance. It's actually it has like a liquid type substance in it, and it just dries over time. So
Oh, there is a liquid in there. Okay.
yeah, like a paste, but yeah. So it just dries.
So it
Like
operates a little bit differently, or it probably degrades differently than a traditional like lead acid battery. I was just wondering because I'm trying to work with the Bedini circuit, and it's good at desulfonation. So I was just, trying to get my head around how the capacitor degrades, and if it degraded in the same way, then we could kind of use that.
yeah, it degrades in a different way, from what I know. And so and there actually is a way, if you Google it, how to rejuvenate electrolytic capacitor. So there is kind of a different process on how to do that if you're interested. Yeah, in fact, there's self-healing capacitors. So I don't know if you've seen the white capacitors that Nathan he has on his
the big ones. Yeah, I got a big I got a big HV 2000 volt, like a big thick white one.
Right. That's a self-healing one, which is pretty cool. There's kind of two self-healing types, and that's one. Wait, so Mike is putting some questions out here. Sorry.
Hold up. Mike talking about his holes again.
He's setting us up for episode 2.
Oh my goodness. That's funny.
Oh, I got another one for you, Mike. Don't wait, I'll show it later. Oh, Mike, that was
awesome.
hilarious.
Just finishing up the questions. Victor asks, what do you make of the thermal picture that showed a hot side and a cool side to the primary? The hot side and the cool side to the primary. That's an interesting question. So if you guys remember, the sphere sits in kind of like a bowl of copper wire, and the copper wire is warms up a bit, but the sphere always stays cool. I think that's what he's asking here. Why is there a hot side and a cool side? I think because the sphere's equator has such a low electromagnetic effect? Oh no, that's not a
Oh,
good
wow.
no. That doesn't answer it either. That's a great question. I'm gonna write it down.
Because you have implosion in the center. You're creating the other side of the energy. That's why I wanted you to put it in clear. It'll become real evident what's going on.
So when the sphere is in the middle cool and it's wrapped around the copper pipe that's warmed up.
So just think of it this way: your regular Tesla coil, the inside of the pipe is a lot cooler than the outside of the pipe, right? So now you've transitioned to 360 degrees. So the center is just going to continue to get cooler like a vortex.
Wow. Good answer. Thank you. I'm always writing down Nathan's answers because they're so deep, and I gotta try to work on comprehending them.
Shan Jack's also someone who sent us a really cool modified Bedini SG without the need of the 12-volt battery, with replacing it with capacitors. He says, I once tried a Bedini SSG for derusting using the spikes to knock oxidation off an automotive headlight socket. That's interesting.
Oh, wow. Yeah.
Yeah.
That's really interesting.
Well, it makes sense. It kills the corrosion in your battery with the Bedini circuit.
Right. There, I was assuming there had to be something else you could do with something like that,
Mm-hmm.
Yeah, that makes sense.
Yeah.
They have a thing that electrically arcs metal and it'll tear off all of the corrosion that's on it. Yeah, they make those things.
Oh,
I think I've seen
didn't know
them.
that.
Yeah, I think I've seen them. Straight dope says he needs a lab coat. So Ben, you've got a following.
We have a whole fan club for Ben.
I started something here. I started something.
Right.
Yeah, you don't need to sell mugs and T-shirts, Ben. Just lab coats
Just
and hard
lab
hats.
coats.
Yeah, hard hats.
Right.
Yeah. It's the passion.
Absolutely.
Though.
Absolutely.
Ben's all in. Ben is all in. That's what I love about it.
That is
Ben,
totally
110%. Yeah.
Totally a
110%.
Ben signature.
That's right. Right. Does anybody know high frequency, high voltage affect pacemakers? Yes, they do. You don't want to have a pacemaker.
That's why I couldn't have I wanted my grandpa to see the rodent coil and the Tesla coil that I had. He's all interested in science, but he's 94 and he's got a pacemaker. So I had to, send him videos.
Right.
Unfortunately.
Exactly. Yeah.
Yeah,
yes, it will. Your hearing aids too. If you're too close.
Yeah, blew up one of mine.
Oh, blew one of yours? Yeah. Yeah. Thank you guys. All the love. Tests should be tested by you. Thank you, Wizard of Woodstock. I'm making a gravity flyer. So I've printed out a lot of stuff from Nathan. I take copious notes. I have a few scratch diagrams. I have an idea, but I'm just not quite done with the geometric shapes I'm working on with the Tesla coils. I'm working on. Have you guys ever heard of the Mobius strip, where it has only one side?
Ooh,
there's a two-sided version of it that when you place it on a table, it just rolls and stays rolling because it has this perfect center of gravity. I'm working on getting a 3D print of that to wind, because I think it's a geometric shape that focuses all its mass into the center, even though it doesn't look like it. So I'm wondering if that's going to have some sort of electrical effect.
I'm sure it would. Yeah, like that's the thing here, is there's so many different patterns and geometries to try. And that's so awesome that we have a whole team now. So it's not like just up to like one or two people who are like in their basements working on this. We have a whole team, and then we can try different things at the same time and get them knocked out. And that's I think the important part. We can get this done faster that way.
Exactly. Yeah. I have a rodent coil jig, so I know where to go to. It's like, I don't have to know everything about it, like, because I have somebody who does, and that's great. And Gravity Flyer.
Yeah.
Nathan will be my big brother with a Gravity Flyer, and it's awesome.
Like if it was just me working on the rodent coil and I didn't have any help at all, I could be working on this for 10 years. You know what I mean? And
Yeah.
not really get anywhere.
Yeah, it's true. There's like a synergy when you get a team together. They just do way more. It's awesome.
Oh, Mike says send him a link.
Mike? Which Mike? Faraday?
I sent one to Faraday already, and we're going to send one to Mike Dawes when we do the video because he has to see it in person. We got to get his live reaction.
Oh, okay, sure. Yeah, I appreciate that.
We got a lot of mics here.
Yeah, 3 mics. So Miniscope, Coat Creative Studios. So I don't recommend Miniscopes other than for like the transistor testing of the different testers. But there is a very inexpensive oscope that I use, and I beat the snot out of it. It always works. So I can give that recommendation, but that scope's probably close to $300. But it's worth it'll keep up with those $800 or $1,000 oscope. So because I don't need all the functionality, but I need something that's gonna be accurate and take a beating. So if you want that, I can put it or give it to Nathan. If you put it in the comments, maybe YouTube or something like that, I'm not sure. And we can get you that info. Or if you rewatch this, you can screenshot my lab because you'll see my test equipment if you want to try that. But thank you so much, Coach Creative Studios. Thank you, Mr. Obvious. Jabber. Awesome. Thank you.
We're going to have to see Jabber's electric motors here soon in the future on one of the next episodes because that sounds interesting.
It does. And I think Crypto has some electrolysis alchemy experiments. That would be awesome to see too.
Yeah, I agree. I love those experiments, man.
Mr. Obvious is asking, when you talk about heavy metal, you talking about Mercury? Freddie Mercury? Sorry.
Yeah.
That's bad.
There
you
go. Putting the primary in the middle has become an engineering challenge for dielectric breakdown damage to the coil. So I've built a fully functioning Tesla coil with a primary in the middle. I really didn't have anything happen. So maybe I should show that. Maybe I'll do a full Tesla coil with it reversed and see what stuff looks like. Stumbled across a binder full of Tesla patents years ago. The feds kidnapped 80 years ago. Yeah, I don't think we have all the Tesla coil patents. I think history shows that some of his patents were not free to the public. Let's put it that way. I have a book of all his patents. Yeah, it's a great read. If you can read 1800s engineering English. So, all right. Thank you guys. Good time. Am I almost through the questions here? Let's see. A lot of guys talking with each other. Great conversations. Yeah, ceramic capacitor goes off. You'll have a broken window. Yep. They don't like frequency. They're great for high voltage DC, but put a ceramic cap on anything with frequency and a little power. Woof. It will take your window out. Definitely. Let's see. 1,100 volts across a 100-volt capacitor explodes. Nothing to do with frequency. That's true. That's true. If you're using a capacitor outside its voltage range, it'll explode. If you use a low frequency cap with high frequency, it'll explode. But there's some kind of wiggle room in these numbers. So it's mostly true, Mike does. Thank you. Let's see here. Bert and Ernie, vacuum chamber. Yeah, I use a vacuum chamber in all my epoxy pours. It makes a solid insulator around my coils, so that way I don't have plasma arcing on the inside. So not sure what your question is on high voltage spikes, Mike. Let's see. Almost through, guys. Have we played around with electrostatic motors? They are fascinating. The Testatica allegedly runs use advanced electrets. You know, an electret is a permanent static field. So an electrostatic motor, that would be an interesting combination. Yeah, definitely. But unfortunately, the word static means not moving. So I don't know how a not moving field would move the motors, but it's a super. Maybe if you rotated the electrets, would it move the electrostatic motor? That would be really cool to show. I've never heard of something like that. Let's see. Never heard of electrets. Yeah, I get Google them. I think even Wikipedia has a good explanation. And sounds like frozen acoustic resonance. Do you think he's referring, Nathan, to when I start turning it up to 100 volts and it goes silent?
Maybe.
Do you remember that?
I think
when
so.
I sent you?
Yeah. I'm
And-
trying to think if it would work in that way or not.
So the closer I got the capacitance and inductance to get to the resonant frequency, I found out that my plasma discharge, which has a good volume to it, you can hear it, it went silent. And I started pumping in more volts. The plasma grew, and yeah, there was no sound. And I think I went from 70 volts to 100 volts, 30 volts higher, and it just remained the same, silent. And in these presentations, getting the sound out correctly is hard because it'll override the voice, or it's like 20 clicks to turn it on and off. So we'll figure something out, but.
Well, hold on. If sound is movement, then sound not moving outward must mean it's moving inward. So it's got to go somewhere, which means you're pulling the energy in from everywhere else. So you got to be pulling the sound in. So it goes into the center of the chamber, which would make it a resonance chamber inside. That would make more sense.
Yeah, that makes sense. I don't put epoxy inside the sphere, so it's.
No, but
there's nothing.
it's getting a field like the Earth. So if the Earth runs on a resonance chamber, you're halfway to proving it by doing your coil.
Oh yeah, I didn't think about it that way. I have to dig more into that, Nathan. I need you to give a longer lecture on it. Good stuff, though.
I agree. I'm a little fuzzy on that topic myself.
Yeah.
No, well, let's just put it this way: I can find resonance in anything because it's in everything, and you just got to know where to look. So, but I'll get one prepared and kind of just go over a little bit, and then I'll just do off the cuff live on it.
Sounds good.
Nice. Yeah.
Thank you, Straight Dope. Is it like nuclear decay? Not sure that question. Self-healing mineral oil. Have you guys heard of that?
No.
Let's see.
We keep hearing about baby oil in the news, but not mineral oil.
Looks like there's a good dialogue going here in the chat.
Oh, there always is.
Yeah, I love it. I finally get to go out at my pace. Being dyslexic, I'm a super slow reader. Good stuff.
Okay, I know how you feel. I might be slightly dyslexic. I have a problem where I read numbers backwards sometimes.
Yeah, that's definitely dyslexia.
Yeah, I just went over my employer called me today because my mileage is all screwed up, and I'm like, yeah, no, I was just talking to my doctor. Like, I might might have some kind of dyslexia myself with numbers.
All right, guys. I want to real quick just give a shout out to a YouTuber that watches our channel, if that's okay, and you guys could take a look at his experiment.
Yeah.
So let's take a look at this because it's kind of unique in what we're seeing here. He's got a coil on the outside, a coil on the inside, and 2 magnets that he takes from a microwave. So I've been watching this one lately, and he comes out every day with a new experiment. And I'll get you guys his channel here. So hold on, let me hit play on this.
Good morning, Internet. Yeah, I wasn't looking for this. I was working on a totally different project. And I was looking to do something very special in a way of a filter. When I've happened on this coil, and now I'm busy with this coil. So I'm going to explain briefly in this video what I did, how I wind this coil. If you go back and watch the first video, not free energy, I'm not advocating free energy here. I happened on this by accident, and I think that I should explore it a little bit more. So I'm going to go ahead and explain. I think I've got a throat in the throat, yeah. I'm going to go ahead and explain. Basically what it is, I took 2 magnets out of an old microwave oven magnetron. I put a piece of PVC pipe in between them, and they fit. The pipe fits nice and snug inside the holes of the 2 magnets. The magnets face each other with the North Pole and the South Pole. The bottom one, North Pole, is facing upwards, and the top magnet's South Pole is facing downwards. Then I used an old HDMI cable. High definition media interface cable, an old one that was broken. I stripped it and I took the wires out of it, but I didn't want to make the wire shorter, so I pushed it through the center of the PVC pipe, looped it around and pushed it through as many times as I could until I could physically not get any more wire through there. So then I decided, but I have to put another coil around the PVC pipe because no transformer in the world works with just one coil, with just one coil on it. Even Tesla coils has got a primary and a secondary. So for my secondary, I used 1 millimeter magnet wire, and I wrapped 150 turns around the PVC pipe. Then I looped the 2 ends of the colored wire together, and I joined different colors. So in essence, I'm forming one long focus. Come on, man, focus. I joined the different colored wires together. So in essence, it's basically one long loop of wire going through the coil with a start, which is the brown wire going in here, and blue wire, the blue one, coming out here going to the transistor. Additionally, I took the green wire, which is not connected to the rest of them, but it runs along inside the coil, and I reversed it In other words, I'm putting the input together with my brown wire, but flowing in the opposite direction, and the output comes back to my transistor, to the base of my transistor. On that, I've also installed a 1.5 kilo ohm, 1,500 ohms resistor to keep the voltage down a bit, and approximately 18 picofarad, no, 180 picofarad capacitor. Then on my transistor, I've got one wire coming out, which stops here, and that will go to my negative of my power supply. My input, or my positive from my power supply, I've connected 1, 2, 3, 4, 5 ohm resistors in series, which means if I connect my power supply to any one of them or in between them, I can actually step up the voltage and amperage input, or I can step it down. So yeah, this is my first explanatory video about this whole thing. I hope you enjoyed it. Please like and subscribe.
All right, guys. I'm going to give the link one more time. This is absolutely fascinating because it's like our coils, okay, in some ways, and in some ways it's not. So I just really enjoy when people do things a little bit different, because the permanent magnets in there causes either compression or it'll cause it to, change the energy field in a different way. But then the two energy fields he's getting from his inner coil and outer coil is absolutely amazing.
Yeah, that's wild. That's very creative. I'd have to watch that a couple of times. A lot going on.
Yeah, I'll put the link in the description right now. Yeah. It's just, I love the fact of how interesting it, just because of fields. I like to play with the fields kind of like you guys do, and to see which one does what. And then when you amplify one, what happens to the second one? And then how do the permanent magnets in there, are they swirling it? You know what I mean? Like you would get conventionally? Are they compressing that center field so there's always like a magnetic value on it? Like if they're, you know what I mean, repulsing each other in the center, or if they're pushing away.
Yeah, you're definitely mixing a lot of magnetic fields. There's definitely pressure going on.
This is him right here. He says he stays away from high voltages. He has a pacemaker. I would definitely stay away from high voltages. People of Planet Dreamscape. Oh, hold on. Greetings. Whoa, what's going on there, dude? Who's messing with my system? All right. You guys want to see that video?
Yeah.
Hello? Is anybody awake?
Hello?
What's up, guys? What happened? Who's messing with your system?
All right, guys. I'm going to put it on, okay?
Can you hear me?
Was that guy trying
Yeah.
to debunk that coil as a free energy thing, or what was he doing there?
Oh, no. He just puts it out that it's not a free energy device, that he's just doing research on it. He's not trying to make any claims. That's all.
Oh.
So, yeah, but guys, check him out, man. I enjoy watching it. So, anyway, all right, here's the new one, guys. Not the same as last week, but here we go. We ready, Shawn? Shawn out to lunch? All right, well, I'm going to play it anyway. Starship Fringe thing. Rewind
Is
it.
this a new one?
Yeah, it's a new one.
Is my mic working?
People
Oh, it
of
is.
Planet Dreamscape, greetings from the Starship Fringe Think Tank.
Welcome to the plant dreamscape.
It's an honor to meet you, Gold Lady. We'll be transporting down to the surface in no time.
I must warn you, Captain. Any random thought during transport may have unexpected consequences.
Gerald, gather the away team and meet me in the transporter room. Guys, try to be on your best behavior. That Gold Lady seems like one of those uptight scientist types.
The elite of the most prestigious scientific communities.
Gerald, I don't think that Gold Lady's gonna like that.
There you go. Well, when it comes to women, as me dear departed father used to say, you can't live with them, and marrying's illegal.
You know, there was something I was supposed to remind you guys about. Something about random thoughts. Huh, oh well, we'll just figure it out when we get there. All right, Ian, 5 to transport.
Nathan.
Oh, that's a good one.
Oh my God.
This didn't work out for us at all. Oh man, have you guys seen Bernie?
All right.
It's gonna be so great.
Bernie's a scarecrow.
Ben, where was Mike? Isn't he usually running the transporter?
Right. So now put one prong in the ground, the other prong in the smaller hole, not the bigger one. The smaller.
Does it matter which one is which?
You know, that's a tough question. It kind of does matter. But anyway.
Wait, so the red
Of the two holes, other than the ground hole, of the two holes that you have there, one is smaller. That is the smaller hole is the power. The bigger hole is the return for that power.
the negative. Okay.
Yeah, you don't want to use that.
Oh my Jesus. Oh. Every time we check on Mike, he has the same conversation. It's hilarious.
I like that Wizard of Oz photo. That was funny.
People of planet Dream. Oh, I'll put it. So we got Victor in there, right?
Well, that was a short one.
Yeah. Yeah.
I couldn't get a good picture of his face because he's always in the dark room. So, just Gerald.
It was a challenge, I know.
Gerald talking Irish, man, was just the most hilarious thing when you did it on the show. So, but everybody's random thoughts. So Gerald is thinking of a lion. Then Ben's thinking of Leonard Bot over there.
Yeah.
And then Bernie's thinking of popcorn. And then I'm thinking of a gorilla watering his lawn, but it looks like he's taking a piss. And then we show Victor over there thinking of wizards. So
Wizards.
I wonder what Ian's thinking about. He's got a big smile.
Because Gerald's talking Irish.
Who's the lion that's all naked?
That's Gerald.
Oh, good.
Remember the lady said, whatever you think about's coming back to, you know what I mean?
Yeah, these are funny. These are funny.
What are you using to make this?
Man, I'm using, what was it? Search of the Sea.
Standard photo editor?
Canva.
Canva.
Oh, yeah, I use Canva. It's great.
Oh, it's just funny.
Canva and a website called remove.bg. It'll remove backgrounds pretty easy too.
I just love it. We can't have any of this, Mike, without you. So I always have to add you no matter where you are.
I want to learn how to do animation cartoons.
Yeah. No, I was I'm gonna when layoff season happens, I'm gonna start Blender. I'm gonna start learning a little Blender, maybe putting some of those in the videos.
Oh,
some 3D stuff.
I
Yeah,
looked at a
animation
lot of
would be
those
nice.
AI,
Learning it.
animators. None of them seem to animate right. It's like,
Yeah, I mean, honestly, you really have to either hire somebody or learn how to do it yourself. And I mean, there's maybe one or two pieces of software that I use to help me, but it's still hit or miss. I'd like to actually learn how to properly animate everything.
I wonder if the cartoons like the Simpsons and all that, was that like hand drawn and then scanned one frame at a time, or how did they make that?
I'm not sure, but I know South Park, they have their own custom software for animation, and it works quite well, but it's proprietary. So,
yeah. So anyway, guys, I hope you enjoyed it. Just another episode. I'll put it in again, and then if you guys want it, man, just let me know and I'll send it to you.
Is it the HD version?
Yeah, the original version. You can change it all you want. I like Mike's version. I watched it today. He's got the beeps and bops of what's going on in the Star Trek show. It's pretty cool.
Yeah. Found it online.
Right on. Yeah, well, captain of the Star Trek French think tank. Oh man, that's so great. Yeah, well, I don't know what happened to Gerald, guys. He was here, and then his thing popped off, and I tried to email him, and I haven't got a hold of him yet. So,
I hope he's okay.
Yeah, I hope so too.
Probably crap. His internet's probably just down. Maybe. Oh, there's Bernie. Yeah, Bernie's having a problem with his internet. Looks like too. He's popping in and out.
Yeah, I've seen that. So I think everybody's just having a little trouble. I hope those cats didn't pee on his router again for Earl. Oh man. All right. Shawn, you still there? I think Shawn took a break.
Shawn's at the fridge.
Right in the fridge in the middle of the show. Nice.
So, Mike, you were asking about a high voltage LED. I knew I had a couple that came with my Tesla coil, and I just found them. So, I also have an update from Mike Morrell about his developments on the coil. And he actually utilized one of Daniel Nunez's modified Joule Thief circuits, which I'm going to be building tonight at some point and testing out. And he got some really good results. So if you want, I can show you.
Hi, gents. I'm back. Thanks for the break.
Right on. Did you see the video?
Just parts of it. But I did start laughing. Something about a cat and a router.
Gerald disappeared on us again, so I think his cat's got his router again.
Too funny.
Oh.
So I caught part of it, how he was mixing electromagnetic magnetism with permanent magnetism with he had some voltage drops, and I mean it was a lot to take in.
Oh, I was referring to the other video.
Oh, no, I haven't.
Oh. I think Bernie's trying to say do it again. All right, one more time, Bernie, just for you. Planet Dream. People of Planet Dreamscape, greetings from the Starship Fringe Think Tank.
Welcome to the Plant Dreamscape.
It's an honor to meet you, Gold Lady. We'll be transporting down to the surface in no time.
I must warn you, Captain. Any random thought during transport may have unexpected consequences.
Gerald, gather the away team and meet me in the transporter room. Guys, try to be on your best behavior. That Gold Lady seems like one of those uptight scientist types.
The elite of the most prestigious scientific communities.
Gerald, I don't think that Gold Lady's going to like that.
There you go. Well, when it comes to women, as me dear departed father used to say, you can't live with them, and marrying's illegal.
You know, there was something I was supposed to remind you guys about. Something about random thoughts. Huh? Oh well, we'll just figure it out when we get there. All right, Ian. 5 to transport.
You put Ian in a quilt.
Nathan. Oh my God.
This didn't work out for us at all. Oh man, have you guys seen Bernie?
All right.
It's gonna be so great.
Ben, where was Mike? Isn't he usually running the transporter?
Right. So now put one prong in the ground, the other prong in the smaller hole, not the bigger one. The smaller.
Does it matter which one is which?
You found the perfect sample. That's a tough question. It kind of does matter. But anyway.
Wait, so the red
Of the two holes, other than the ground hole, of the two holes that you have there, one is smaller. That is the smaller hole is the power. The bigger hole is the return for that power.
the negative. Okay.
Yeah, you don't want to use that.
Oh man, that's absolutely hilarious.
Love it.
Oh, it's always funny. Mike's in the lunchroom and still thinking the same conversation in his head. Oh, we're gonna have to keep doing this, guys. That's too funny.
It is. It's great.
Oh,
Too much fun.
we'll have a little mini series before we know it.
We get Shawn in there at the helm, running the laser spark, shoot at the Ferengis.
Yeah.
Oh man,
Laser, what do they call the tractor? No, laser beam.
Phasers or
Phasers,
tractor
yeah.
beam.
Phaser beams.
Yeah, the Star Trek guys carried phasers.
No, the ship has a laser gun.
reflector dish.
I think it's phasers too.
Yeah.
And it has those what do you call those other things? Those timed bombs or whatever.
Photon torpedoes.
There you go.
I'm not a Trekkie though.
You are now.
Photon torpedoes. Load the
Yeah.
photons. Was it photons? Yeah. Light.
Yeah.
Light bomb. It's a light bomb.
Oh.
How about
Yeah.
that?
All right.
Great old show.
What
So-
has Star Trek not predicted? I mean, they probably even predicted the light bomb.
Yeah,
the photon torpedo, whatever. The light torpedo.
something with no mass being an object of destruction sounds interesting.
No, well, light has mass, energy mass.
For some reason, they say photons have zero mass. That's why they can go as fast as they do.
It's got to have mass. It's got energy.
Yeah, that's the
It keeps
standard
changing
model.
every year. It's something new. Like just this year, they saying that the Big Bang was not the first event, and there was a bigger explosion before that one.
Yeah, you know why the Big Bang is crumbling is the James Webb Telescope. It's allowed us to use infrared, and it's 1,000,000 miles from the Earth, so it's in a real dark spot where they can see through all the dust clouds. And they were expecting to see some kind of primordial part of the universe where just right after the Big Bang, they were going to see, old type, what's the word? Just the beginnings of the Big Bang. And what they found was perfectly formed galaxies and stars, just like we see all around us today. So now they're like, oh boy,
What?
James Webb can
What?
see.
Did you just say what I think you said? Before the Big Bang, they found perfectly formed galaxies?
Sorry.
crazy.
So they're supposed to see so deep in the universe that they're going to see just after the Big Bang. And so they wanted to see star formations and galaxy formations that were primitive, because now we live in like the Milky Way. These are more advanced, complicated.
Instead, they were all already formed.
They were just as good as informed and complicated as everywhere else.
And
So
they,
now
how did they
they're
even see
rethinking
that?
it. So the further you can see in the universe, the further back you're looking in time. Because let's say you're looking
I
back.
mean, my question is, how could they see past the Big Bang? You know, that shield or that energy wave.
I've not heard of two Big Bangs. That's probably very new. I just know that the Big Bang's falling apart because they were hoping to see a lot of their theories
So
come
they're
to
not seeing
fruition.
through the Big Bang. They're seeing through something else.
So they're not seeing the Big Bang, but they're seeing further into the past. And all their models show that there should be certain things, and none of it is what they're thinking. So also, too, there's a really good new theory on gravity that's coming up. And what's hilarious is, what's that?
Yeah, what's your understanding of that new theory?
Well, I just heard it yesterday, so I won't do it justice.
Okay.
But I can say
What did you get out of it?
What surprised me was that a guy tapped into 0 point energy. And by the way, this is a prominent academic physics and physicists, and they're not the fringe scientists, but this, as the standard model falls apart or looks ridiculous, quantum mechanics and so on, there's a new theory that can link the small to the big, which has always been the problem.
You see that? You see that? What Quatrin just wrote? We're in a brain. That's a.
Are you talking about a Boltzmann brain or Boltzmann?
He's saying that the whole cosmos is inside of a brain.
When they say brain, they mean like membranes. So if you could think about a room with a bunch of rubber curtains, and if you pass one rubber curtain, there's another rubber curtain. That's what they mean by brains. It's BRANE.
Layers.
Right.
So wait, so they got this James Webb out there now far enough, and they got it up and running so they could see further than they could see before. So essentially, the furthest that we could see in the past was considered the Big Bang beginning.
Yeah. So,
and now that we can't see the actual Big Bang, because they had some kind of reading of an image of the Big Bang that they presented to the public. I don't know. Looks like a big globe, bluish colors, and kind of like the TV static, but not.
Oh, you're talking about the universe's microwave
the Big Bang
radiation.
signal. That's what they called it.
It's leftover. It's leftover microwave radiation from the Big Bang.
Right, there you go. That they said was from the Big Bang.
Correct.
And now they're saying that it's not from the Big Bang, but they still
Victor.
have the radiation background thing. And they don't have an answer for that. Now they're just going to abandon it. Oh, the radiation background doesn't exist anymore. It's still there.
They're just, so my daughter is a physicist from Northwestern University, and so we go back and forth. And one thing she told me was that there are a lot of infinities, a lot of assumptions in designing the standard model and our basic understanding of cosmology and the universe. And she always wondered why there were so many assumptions that it can go different ways. And it started to become smoke and mirrors to her. So I guess it's not too difficult to incorporate these new theories as long as they can get some experimental evidence.
I just hope that image that they called the leftover radiation of the Big Bang is an actual real reading. And if it is, why do they navigate away from it? It's got to be part of this whole, telescope thing that they're seeing past that radiation layer now. They're seeing past that particular, is that what we're saying here? That they have able to see past that particular radiation layer, or they're just seeing further than they've been able to see before?
That's a good question. So we'll start with the background microwave radiation.
Because
That's
they're not
over.
using a telescope to see the radiation. They're using other instruments to do that.
Right, correct. We have radio telescopes that just see with radio signals. We have every kind of telescope. So they just call them telescopes, but you're right. They're not the see-through and the visual.
They're not lenses per se.
Correct.
Of-
Okay, hey Sean, I think I found the resonance frequency of this thing.
Oh, you did?
Yeah, I think I'm on it.
Awesome.
I mean, I'm not sure how that James Webb was it. I don't even know how that lens is, if it's even glass or what technology they're using to do that.
It's about the size. The lens is about the size of a tennis court, and it's a bunch of beryllium, I think, gold-plated octagons or hexagons, and they arrange themselves to make one giant lens.
That's interesting.
Nathan's got something. We're ready to go.
Sounds like they had to launch a bunch of times to get all that stuff up there.
I can tell you facts about it, blow your mind. It's so crazy.
I don't follow this kind of stuff. I don't know why. I'm totally interested in it, but I don't dig into it. I don't know why. It's busy with other things. You know?
Yeah, I mean,
I just
everybody
think
has
they
their
should put it
interest.
more publicly out there and more available, like, you know, for people to know what's going on in the latest, you know, developments of technology in general and discoveries, instead of proprietarizing it all into shows and that they can sell to cable subscribers. It should be public information, like right away, not later.
Well, I've been waiting on the James Webb telescope for about 18 years now. So I just been so interested in the new telescope that is going to replace Hubble.
Yeah, I kind of gave up on all that waiting. I'm 50, so you're 50 something.
I'm
and we're in the
54.
same- Yeah, so we were in our 20s sort of when they started launching these telescopes, and we were given the hopes of, and those hopes came true to a large degree, you know, over the next 20 years of all the imagery they gave us, and all these things we were able to see now that we couldn't see before.
Yeah.
And it's not stopping. That's the whole point. It's not. That's the crazy thing. They're advancing. It's not seeming to have an end. So
No, there's too much to know. It's there's a lot of cool stuff out there that we're still just discovering. So
I would like to know how what kind of instrumentation they use to detect the background radiation.
Probably microwave radio telescopes. They're these giant dishes. They're like 200 feet in diameter.
Oh, that's right. It was microwave background, right?
It's microwave background radiation. It's so puny low that only a sensitive instrument can detect it. And they construct this sort of oval-looking. You've probably seen
microwaves are all super high frequencies, or do they range? Or
yeah, definition microwaves are in the gigahertz range.
Hello, hey guys.
So is it
Hey,
steady,
Nathan.
or is it
It's fascinating as all that stuff is, guys. John, I need your help real quick.
Who, me?
Yeah.
Okay, what's up?
So I need you to look at the numbers here. Escape. Greetings. All right, I've had enough. I've had enough. I don't know how that thing. Now it's gone. Okay, now here we go. I have 21.46 on my volts. And I have 1.037 on my amps.
Okay.
And a resonance frequency of between 306 and 310. So I'll call it 308.
Yeah.
And I got light up at about 2.5 feet out. And I do have breakout. We're in DC.
Yeah. The quasi-continuous wave. I see it. What's your voltage setting? Is it 22 volts?
No, it's staying steady. It's
what was the starting voltage that you started with?
I started right there.
21.4. You start at 21 point.
Yeah, it's only going to go up on the second decimal point. It
Can you
goes.
put,
It's
like,
fluctuating.
Can you see? Okay, so you can't put an even number in there, like 20 volts.
Hold on,
or
let me
it'll
see.
fluctuate.
Just give me 1 second.
Sure. I mean, your amps look like in a safe range where it is oscillating. If you recall, as long as the voltage is steady and the amperage is in that 1 amp milliamps range. Look at that, it's 0.9 amps right now, 20 volts.
Yeah, voltage is steady.
Yeah, it looks good. So what you're seeing here now is your voltage is steady, your current's in a decent range, and you got a breakout on the top of your Tesla coil. So but because the breakout is not huge, that's the room you have for tuning. And so it's not necessarily that you're tuning to have a huge breakout. Huge breakouts are great, but you're more in tuning to see how efficient you can get it to run, because then you'll have a lot of plasma at a very low power, and that opens you up for other experiments.
So do you think the setting is just a little bit off?
Yeah, I think so. Are these the same capacitance you had for your other ZVS?
Yes.
Yeah, so I figured that the capacitors wouldn't work 100% because it's a new ZVS board. It has a newer design, has less diodes, has less resistors. So the new ZVS is not quite going to work like the old one that you had tuned. And so what I would do is, so for example, what was good resonance that you were picking up on your O-scope when you were using the old ZVS? What was the frequency?
You would set it at 307, and that's in kilohertz. And then it would drop once it started resonating.
But so when you connected the little antenna to your O-scope probe, and then you turned on your Tesla coil when you're getting those 10 inch sparks, what was the antenna picking up on your O-scope for frequency?
That's what I just said. It was about 307.
307?
So we're just a little bit off right now.
What are you picking up now?
Sorry, you can't really.
No, it's cool.
That's a nice clean wave.
It is. You're getting 310, and so
we're just a little off.
Yeah, I mean, yeah.
You guys go ahead and talk, and I'll adjust it just a bit more and see if I can't get this thing up.
Sure.
So I looked at the ZVS circuit. It's got those capacitors. That's what helps the wave build and drop slowly, like that. And they use a flyback to trigger the next pulse or whatever.
It's not a flyback. It's a tank circuit. So if you connect a capacitor and an inductor.
No, they're not. I don't think they're using the capacitors as tanks, even though it can be. It's filling up slowly, but yes, it does pulse, right? But I think they're using the flyback the opposite direction to trigger the next event in the next pulse in the ZVS. But the capacitors are there, so the voltage rises slowly, and you get that sine wave curve.
So
so that you also get the same drop slowly. And that's from those capacitors. The two capacitors. One capacitor handles the top half of the build of the sine wave, and the other capacitor handles the bottom half fall, or I don't know if you'd call it a fall, but yeah. And it keeps the voltage rise and fall even in a curve fashion, so you don't. And it also prevents it from creating spikes in that way.
So So you're sort of describing more of a
But there is a
traditional.
flyback pulse. It's not a
It's-
spike per se. It's a
No,
smaller pulse.
it has nothing to do with flyback. Sorry, I think you're talking about something else, Mike. So you
The
have two
ZVS has coils,
MOSFETs.
correct?
You have two MOSFETs. When you apply a voltage, because there's no two perfect
You
transistors,
got more than two MOSFETs.
one of them
in there.
turns on.
You got a lot more than two MOSFETs.
There's only two. When you turn one
No,
turns
I mean,
on,
there's other components other than two MOSFETs. There's coils and there's capacitors.
those round coils there are chokes. That's just for a ballast to make sure the current is steady.
Yeah.
The capacitor, the two capacitors form a tank circuit with the primary of the Tesla coil, and that creates the oscillations that then resonate with the secondary of the Tesla coil. And when it reaches the resonant frequency.
That's what I was saying. Your oscillation has a curve.
Sure, but it's not a rise and fall time by capacitors. That's more of a power
The capacitor controls that steady rise. Isn't it powered by DC or AC? I can't remember.
In a power supply, you're correct, but not in a ZVS.
Is it powered? Is the ZVS powered by DC or AC?
Both. You can choose which one you want. The only thing is the AC, you have to filter out the negative part of the sine wave.
Mm-hmm.
So if
why do they rectify out that half? To make the DC pulses. Okay, gotcha.
I rectify it out because I like the cool sparks.
Well, they get a DC pulse when you do that.
Exactly. It's only the positive, so it actually stops and then
and where's that DC pulse going? Into that choke coil.
Correct. The chokes are prevent from large current spikes and blows up your ZVS.
And it also enables them to get a lower voltage that they can use to trigger the next I don't know if it's pulsing or oscillating, but I think it's depending on if you're using DC or AC.
It's oscillating, it's not pulsing.
Right, if it's oscillating and they're using AC, so then that coil is still being, the AC is still being clipped, right, on the way in.
It just resists changes in current, so your current's going to be out of phase from your voltage because it's going to cause a lag.
The diode is the AC being clipped on the way in?
No.
Oh. See, I've never worked with a ZVS, so I just seen the circuits, and they look very interesting.
I've been looking for a high voltage oscillator for a long time, and this is, I think, the great. Yeah, I think it's the great.
You change your cap size to change your signal.
Exactly. So the steps to get your ZVS working is you measure the inductance of your primary coil, and then you take the secondary coil. These are of the Tesla coil, and you determine its resonant frequency. So that's a separate bunch of steps. And then once you get the resonant frequency of the secondary coil and the inductance of the primary coil, then you can put it into a calculator on the internet and it'll come out with your capacitance needed. And so those are the steps. And so I'm going to be presenting on these steps. I'm going to try to simplify them so everybody can build their own, I don't want to even say Tesla coil, but their own high voltage plasma. And it doesn't have to be dangerous. I shared with you in the presentation that I was only using 6-7 volts AC, milliamps, and yet I got 2-inch sparks and it was fun and I can experiment with it. So, but yeah, those are the 3 steps. 1, inductance of the primary, which is that copper pipe. 2, the tall tower of the Tesla coil, which is called a secondary. You get the resonant frequency of that, and then the calculator will spit out your capacitor size. Once you get that capacitor,
I think the capacitor is there to help, because you're never going to get the 2 coils exactly right just to have them resonate without a capacitor. You need the capacitor to make up for that small amount of difference.
It's the key component. Otherwise, you can't get resonant frequency. When the capacitive reactance equals the inductive reactance, they cancel each other out, and then you get, well, on paper, you get infinite current. But because there's no perfect capacitors, inductors, or even the wires have resistance in them.
Yeah, because when they cancel, it also seems to simulate the removal of resistance.
It doesn't simulate, it does. It removes resistance.
Well, it's all the amps that flow like crazy.
Right. And so it's what is called a
but that's only when they're canceling, right?
Correct. So think of think of a capacitor like a resistor. Okay, so if capacitor 1 has 100 ohms, and by the way, capacitive reactance is measured in ohms just to make it confusing, but so let's say the capacitor has 100 ohms of reactance, and then the inductor has 100 ohms of reactance. Well, their reactants are 180 degrees out of phase. So boom, they cancel each other out. Boom, you have it.
Oh, right. That's a good way of putting it. I didn't look at it like that. Right. That makes sense.
And that's the cool thing about the ZBS, because that's what I don't know if you caught the part of my presentation where I grabbed some balls of wire out of my used wire bin and built a primary secondary coil that oscillated.
Uh-huh.
Did you catch that part?
What, today's show?
Yeah.
I was half an hour late.
Okay, yeah. I'm taking balls of wire out of my junk wire bin and throwing them on the ZBS, and they oscillate because the ZBS is, I think someone said here in the chat, ZBS is the new kid on the block. Oh yeah. It's strange how it's so powerful.
I gotta say, I do, between two pulse systems, the ZBS and just the standard switch of a coil, I like them both, and I don't think either is going to go anywhere. They're very important because one is, you got capacitors there controlling your rise time and your fall time, and the other one doesn't have any of that. It's as sudden as possible, the switch,
So you're talking about power supplies again. I think
guys,
you're talking about power supplies.
Switching wise,
Hello. Okay, Shawn.
Yes.
Remind me real quick. I know you guys are having fun. I want to go to AC now. So, which wires go where? The two diodes go to the negative or positive?
Two diodes go to the negative, and the cathodes are faced away from the variac.
That the half bridge rectangle or whatever, full bridge rectangle.
I
need to get a variac. Right. I don't know why I don't own one. They're just too cool to be able to vary AC like that.
They're cheap and they're awesome.
Yeah, they are cheap. I still don't have one. It's ridiculous. I mentally smack myself over this thing. I had a lab for like 4 years, never got one. Just
Yeah.
Could have been making all kinds of DC or an AC or whatever.
Yeah, it's awesome. Yeah, you can build your own rectifiers and clean up the AC, make a DC. Get a 30 amp.
It might have something to do with the fact there's 120 volts in the wall already. I don't know.
All right, guys.
You settle for the 120, but if you want a lower volt AC, that comes in handy.
Yeah.
All right.
How's it going?
So, all right, you ready?
Wait. My the cathodes, are they pointing away from the ZBS? Cathodes pointing away from the ZBS?
You mean the power?
Yeah, they're like under 50 bucks.
The diodes, sorry. The diodes, are they the cathodes pointing away from the ZBS? How about this? The cathode on the diode needs to be pointed toward the variac.
Okay. Well, you lost me. Where do you
Okay,
want
the
this
gray
thing
ring.
sitting?
The gray ring on the diode. Can you pull it up? The gray ring.
Yeah,
on
those
the
are
diode?
set where exactly where you set them.
The gray rings are away from the ZVS.
Yes.
Can you?
Yes.
Okay. Awesome. I just didn't want you to fry something. Okay.
Hold on. No, they're not, because one side's away and one side's towards it. You're talking about
Not on
these, right?
Not on the board. Do you know the diodes that power from the variac?
Okay.
Go to the variac, pull the wire until it comes up to the ZBS. Are there diodes in between there?
Yeah, it's just the way we set it before.
I just want to make sure.
Yeah, I got it set the same way.
Gray rings are down?
Yeah.
Okay, perfect. Sorry, I just didn't want to see you fry it.
No. I kept it the same way. I don't touch that. So we're hitting 10 right now. Let me just point it so you can see this.
Oh, beautiful.
So I'm going to go up to 20.
Your primary doesn't look stable.
We're not in resonance then?
It just needs some more tuning, because do you see how it's blinking on and off the back signal?
Yeah.
That's your primary. The squiggly line that gets bigger toward the right, that's your secondary. It's resonating,
but it's not in
resonating.
tune.
It's not in tune.
Okay. All right. Well, that's fair. So I need it to be very clear on the signal then, right?
That's one way to do it. Another way you can do it is, remember I told you the volts peak to peak? If you're looking on your the screen of your oscilloscope, there's frequency, there's voltage peak to peak. It's called VPP. You can look at that, and as that number goes up, you're getting closer to resonance. Or a simple way is, as you start to lower the capacitance or raise the capacitance to tune it, just look at your breakout. If you're getting bigger sparks, you're doing it right.
So do you want me to go back to DC or stay in AC?
I mean, were you getting a breakout with the AC?
Yeah, I get a breakout with the AC.
Yeah, I mean, let's stay with the AC. I'm curious. So, are you looking to talk about some of this? I'm sorry, I'm lost.
Shawn, you're here. I got a Tesla coil. We need to tune it.
Oh, I see. Okay.
I mean,
let me say a little bit here to Nathan. So Nathan, get it running. Put it on voltage peak to peak, like Shawn said. Slowly turn it up until you get your maximum peak to peak voltage, and keep turning it up until that peak to peak voltage starts to decrease. That's when you're going out of resonance. Then you want to back up to where it made its peak. Its maximum peak is resonance.
No, I understand that.
So long as it doesn't blow.
So
then you have resonance.
Thank you, Mike. It's close to that,
Maximum
Mike.
peak to peak is resonance.
It's close to that, Mike. Thank you for that. So when the capacitor and the coil 1, the primary, they oscillate, okay? They need to oscillate together to make coil 2, the secondary, to resonate at its frequency, and then that's when you get the big plasma discharges.
Okay.
So,
all right.
Yeah.
I understand the theories. Okay.
Okay.
I don't need that right now.
Yes.
We are simply putting a wire in a different direction to see where it oscillates. That's the only point we're at right now.
Resonance. You want resonance.
Okay.
Are you talking about putting the wire down the center?
Right? To tune it, you need to tune it to resonance.
Okay, listen to me. Just stop. Listen to me. The only thing we need to change is where the wire is placed on the number 1 coil. Then we can find resonance. Now, The O-scope is a tool to get there. All I need to know is very clear, direct information, not any theory.
Yes,
I'm
correct. The
trying
O-scope
not to
is
give you.
your guide to see resonance better than on the screen. In reading by the
Never
peak
mind.
to peak is how you see it. The maximum peak voltage that you get out of this system is your resonance point. Whatever you can tune it up to get the highest peak voltages, top and bottom, the plus and minus on your signal, and keeping it steady and clean, that would be resonance.
So
But
so
you want to slowly
Nathan,
turn it up, slowly.
Nathan, you still
Yeah.
got me?
Yeah.
Are you looking to move the alligator clip on coil 1 to tune it? Is that what you're saying?
Yes.
Yeah, apologies. I thought you wanted me
that's
to do the
something else.
capacitive tuning.
No, because I can't because I don't have your little meter, so I have no idea how that works until I can get
Oh.
that.
Gotcha. Okay,
So I have to do old school, move the clip.
no worries. The good news is you're close. So, does the clip just have on the input and the output of the primary pipe? Or is your clip in a certain spot on the pipe?
Okay, hold on.
Shawn, what's the clip? Is that his ground or something?
It's the primary connecting to a tank coil to the primary capacitor.
Hey, can you see it better?
Yeah,
Hold
I
on.
can see it.
Okay, you see it here?
Oh, it's like a signal.
The other one's connected on this
Yes.
side. So we're
Mhm.
connected correctly. It's just not in resonance yet.
And can I see your breakout? Just to see how far out of tune it is. You put in like 40 volts. Can you put in 40 or 50?
Yeah, our breakout's terrible. Hold on. I can't run that. I'll blow them offset again.
Yep. Okay. Should have a little fan down there.
Oh, hold on. I might have a. Just give me a minute.
Sure.
I was trying to tell him to get a nice thick piece of aluminum and use that as his heat sink.
It might help if I connect the ground.
Oh no. That's good feedback for no ground. I don't get feedback without ground. Dang.
Okay. Now. No, we're out. We're out. Okay.
Okay. Is your red light steady? Is your red light blinking?
I can tell you right now we're way out of it.
It sounds out.
Yeah, it's way out. Lord.
And you're yeah, I think you fried a diode or a
It sounds like a
MOSFET.
transient switch gone bad. Yeah. You hear that snap?
No.
Yeah.
We're out of resonance. That's it.
Okay.
It's okay. Yeah. All right.
Okay, turn it on low and show me what your oscope on a probe says when it's turned like 5 volts AC. Just something small where it doesn't fry anything.
I wonder if they have an O-scope that hooks right up into the computer so you can just directly share the signal on the live streams.
Yeah, it's still all over the place, Shawn.
Yeah. Also, too, the squiggly line in the middle is flat now, so it's not, your secondary is not resonating at all.
Yeah. Okay. Well, I guess I'll have to go back to the drawing board and fix this thing up.
Nathan, if you want, we can do an offline StreamYard and we can just go through all this step by step if you're cool with that.
Well, yeah. Usually, look, I could find it pretty easy. I haven't had time today, and it gives you guys an opportunity to help out and figuring this out. Right? It's just a lot of cross information, and it does nothing but frustrate me.
Yeah. I'll be quiet next time. Sorry.
Oh no! It's not that. It's when all you have to do is move
Nate.
one wire. All the theory
Yeah.
in the world, you could take that, throw it in the trash. Okay.
Nate,
But when you're moving
How
one
much are
wire,
those
you just
small
need to have
parts?
somebody who understands it in a feel way. You know what I mean? Or you're hitting it right, or you're getting there. You move it left, move it right. You know what I mean? That's it.
Yes.
How hard is it to change a MOSFET on a ZVS? It can't be that hard, and they're cheap MOSFETs.
Yeah, if you got a bag of them, it'd be great. I could blow them all day, but I don't.
They're like, what are they? $2 an each or something? Like
Yeah,
a couple bucks. They're high amperage though. The thing is, if they get hot, even though they're high amperage, they're still going to go bad and still run, but they're not going to run great. And that's what fools everybody. It fooled me for at least a year. I was having with one of my oscillators or whatever. I was wondering what's up with this thing. You know, wasn't performing like the other ones. You know.
Are you referring to what?
It was it was just a bad transistor that was partially working, or let's say it was 90% good, 10% bad. That's all it takes.
Was it a MOSFET?
Yeah, and they'll run and run and run, but they'll run, you know, deficient. You know, like they're not switching right. You know, people don't realize that they're not switching evenly. You're not getting an even spread in your pulse or whatever signal. And that's what it is, and you know, but they'll run, and you think everything's fine forever.
I've not run into that, but thanks for the tip.
Yeah, I've put together probably 24 pulse motors, and just they're all in parts now, but you know, had them all running all at the same time, and you know, a couple of them would just at a time would just be like not running that well. You see, like it took a little bit more time to start up and all that stuff, you know. And I got the feeling that something was up, you know, with the switch, you know, itself.
Yeah.
So I started just changing the transistor, and bing, the thing's running like healthy again. From there on, I was like, I didn't even doubt it. Next time I had an issue, I just changed the transistor. I don't even ask questions. You know, I've been an electrician for 30 years. I can tell you I've changed wall switches in the thousands, you know.
I might have to go back in the video.
Customer says my light's flickering, I don't ask questions. I go change the wall switch, you know.
Yeah, Shawn, you had a method of testing the MOSFETs, and I have to go back because I missed that part of the video.
Yeah, it's a small meter.
They're cheaper than regular wall switches.
Yeah, it's a small meter on Amazon, and it has an auto function, so it'll test your MOSFETs, transistors, diodes, and everything. So it's pretty cool. Yeah, are we connected over Facebook Messenger? Oh, I can email it to you. I'll email it to you.
Yeah, I have a Facebook Beneficence TV page as well.
Okay.
I'll put that in the chat.
And then, you know, I didn't want to keep changing these transistors, so I started putting, you know, insulators and heat sinks, and I was running them without any insulators or heat sinks. And you know why they kept going back? Because they kept touching it while I'm grounded and stuff. I think that's.
Oh, but I do have some updates on Michael's coil if you want to hear about that. If we're looking for something to talk about.
Yes, please.
All right, let me pull it up. All right, so I'll read you what he wrote me, just to describe his setup before I play the video. Give me 1 second. Circuit. I'll make sure I have it downloaded. Okay, good. All right, so he said he was playing with the Daniel Nunes old circuit, the one with the transistor. I guess it's a modified Jewel Thief circuit. It's the one from the video that we see in Randy's Donuts, the documentary. And I'm sure there was a longer video on YouTube that probably got taken down, but this is the only clip that I've managed to see of it. And it does quickly show the circuit. He takes the coil and he hooks it up to one of those big antennas, those old TV antennas we see on the roofs of some houses and buildings. And he uses that circuit and kind of rectifies the signal into usable power. And he's using a potentiometer to, you know, tune into the right frequency for the coil.
Oh, wow.
Which is pretty cool. Yeah. So you see like a little flash of light. And so what Michael did was he used that circuit. And he said he was at 1.25 kilohertz using 15 volts and 220 milliamps and getting 200 volts output, just like what Daniel was saying.
Wow.
He said, yeah, that's extraordinary. That's a 10 times voltage output or around there, like he he was claiming. That's actually
just
more.
follow Ohm's law. That's all I can say on that.
I had to change my scope probe, so 10 times. VRMS is showing 50 volts. It says at the top it's 212 volts, which is more precise. The neon light is on with a slight blue hue, but he said it's not showing in the video. But this is the circuit that I'm going to be working on tonight to see if we can get it built. And I'm going to show you the video right now.
So Ohm's law, voltage goes up, current goes down. Remember that.
But right, but you said what?
Sounds interesting. Awesome.
Oh yeah, yeah. No, what's really cool though is look at this waveform that he's getting. Look at that on the top. Doesn't that look familiar?
Nice negative spike. I don't know how he did that. That's interesting.
Yeah.
H-wave.
That's exactly what mine looks like on the
top. Not in the
top.
positive, like you don't have a.
Yeah, he said he's not using any tone generator. It's just the circuit producing that frequency.
What I'm saying is the Bedini SG does that, but inverted. It's at the top.
Oh, look at that board.
Yeah, so I do have the circuit here, and I'm going to put it in the preliminary guide for people, because this probably will be going in phase 2 guide as well. But yeah, he sent me the circuit.
It looks a lot like the Bedini circuit.
Yeah, it's a modified Joule Thief circuit. I guess Joule Thief is a Bedini circuit, I believe, right?
Yeah, they're all kind of like similar to the Joule Thief.
Yeah. So, and he said he used they have, if you, it's hard to see in here. You can see it in the image that I'll share later. But you can see the transistor is a PNP. But he said he used an NPN, and he was getting that result, and it worked just fine. So we're gonna try our NPN. It's an E13005 or 007 transistor, the one that Gerald recommended for his protection circuit.
This is the new Nunez circuit?
This is a modified Joule Thief circuit to work with the coil. You can see the channel A and channel B there.
Coil, sorry, the POE, right?
Yeah. And this is utilizing, I'm assuming this is utilizing, I haven't looked at it thoroughly, but it looks like it's utilizing the Nunez method, the open circuit method.
That's what I was trying to tell you earlier, to pulse the coil with flyback, not with square waves.
Right. But and this is a way
to square waves to generate the flyback and throw that.
Well, even having a PWM or a signal generator in the circuit is going to add a lot more, or is going to reduce the efficiency of the system because it's going to consume power, right? So what we want is a simple circuit to produce the right frequency like this. That's not going to consume too much, maybe like mostly passive components, if that makes any sense.
Passive meaning not doing a lot of work, like just
right, not needing a lot of energy to do what they're doing. Like it's not going to be a leak in the system in terms of when we're measuring the efficiency.
The coil would that's kind of saying the coil would have a lot of impedance to it, so it's not drawing a lot of amps.
But this is very good news, and I also have some good news regarding the version 3 432 coil he's trying to work on right now. And we've been going back and forth because he had to wind it a couple times, and we were looking at the photos, and let's see if I can pull this up. And I mean, I guess he had the same revelation at the same time I did, because I was looking at one of the photos, and I shared this with him, and he's like, yeah, that's kind of something that I confirmed when trying to wind this thing, is that there's 3 channels for the advanced version 3 432 coil, not 2. So there's 3 channels on this thing, and
wow,
and that's very important when winding it, because instead of going 1 over and 1 up, you're going to be going 1 over and 3 up, and you're going to be doing that 3 separate times, right? Because you're laying these down individually instead of in a multifilar.
Yeah. When you say multifilar, Ben, are you talking about 2 wires
twisting
going
them up?
in?
Yeah, twisting them up in the bundle like you see in Nathan and mine, and I's coil.
Yeah, you know what, Sean? That term also confuses me because it's like, yeah, you have
So
a
I can show you.
multi-filer. Is it in parallel? Is it in series?
there's
How
the
many ends does it have? You know?
So there's the kind of like a multi-filer,
Wow.
where it's like twisted together.
Is that Litz wire, or is it just one wire going in, the other wire coming back?
So I'm not actually sure
That
how
would
he
be a
did this
series
one.
wind.
This is something unique that he's working on, I think.
It looks
I
like a
haven't really
series
asked him
wind.
too much about it.
Yeah.
But he just, he graciously shared what he was working on with me, and I found this very fascinating. I'm not actually
Yeah.
sure how he wound this one, though. I
I
have to
think it's
ask him. This
series,
is
Ben.
very,
It's a series wind. It's multi-filer,
Yeah.
but you have
but you haven't.
they're
Yeah,
all they're
different
all put in
channels.
series. All the filings.
Yeah, I think you're right, Mike. And then I think that's all the pictures I have from him.
Looks
Do I have another
amazing.
video?
It's a lot of
That
work.
would give you an extremely high voltage, and it'd be easier to wind that up and build it in a multi-filer fashion rather than one
Oh.
piece of wire.
He got the induction working. He got it working as a Tesla coil pretty much, and this is something that I was working towards, but I didn't get around to yet.
Yeah.
And as you can see, look at this. This is with the modified Jewel Thief circuit. He's using the big coil as a driver,
Oh.
primary coil, and then the small
Yep.
coil is just. He said the field is about 2 feet, so
Nice.
it's like a Tesla coil. You
Yep,
don't even have to
yeah.
sit it on top.
Exactly. Yeah.
It's so cool, and those are
is
high
super
voltage,
cool.
I believe, right?
I mean,
Yeah, look at that.
I mean, he's probably getting like maybe, like you said, hundreds of volts.
Yeah.
If and the
But do you
reason
see how
you're
it's in the
not getting-
negative, the voltage? There's no positive portion. Very little positive.
So yeah, in fact, what he's just doing too is he's doing wireless energy.
Mhm.
So I'm curious, other than the coils, what are his other components? Was that the circuit you showed me earlier?
Yeah, just the modified Bedini
Yeah,
Jewel
he's just
Thief
pulsing
circuit.
it like a standard coil would be pulsed, but because of the
And
coil
he's-
geometry, it's negative
Yeah.
portion on
I'm
the
sorry,
spike is
Ben.
super,
I couldn't
super-
hear you. Ben, I'm sorry, I couldn't hear you. What was that?
Oh no, I was just saying. Yeah, he's just putting power into it. He's not putting a tone into it or anything. That just connected to the Jewel Thief circuit. That's it.
Where the oscillations come from?
I'm assuming the frequency comes from the circuit and the components in the circuit.
Yeah, I just
He doesn't. Does he? He doesn't. His load is the LED.
Yeah, yeah. There's another video I haven't had a chance to look at that he sent me as well. I'm gonna put it up.
I don't know if you can get a reading when the LED's hooked up. He probably did that reading when the LED was disconnected. He was reading the flyback.
Wow.
Mm-hmm. Yeah, like
reading the
you
coil
said, Mike.
output.
There's a big spike on the bottom.
There it is. That's
It's
the
it's a
neon.
different. Yeah, it's a different
That
waveform.
bulb is the
If it works
NE-2.
like
You need to get some of those, Ben.
right, but the important thing here is that that's the waveform we're looking for the Nunez method, 10
Yeah.
times voltage output.
That's-
right?
that's the
I was
radiant
not
spike.
able
That's
to
what they
find
call
that.
it.
That's
Wow.
what, and he
The
found
flyback.
it, and that's what we're going to be looking for.
That's awesome.
They call it
Yeah.
flyback too.
You're doing something. It's basically you did a rodent Tesla coil. That's way cool.
Yeah. Yeah. And Mike's doing amazing work helping me trying to decrypt some of this. And this is going to be all great. This is all great news for phase 2 and phase 3 of testing of my coil specifically. So
That's
we're
great.
gonna have a lot of fun with this, guys. And the revolution has already started. There was some talk saying, I had some word around the campfire saying, it's impossible. We're never going to inspire people to start building these devices, and we already have. So
Yeah,
it's happening.
I know. I have a one I'm winding right now.
Mhm. And I get contacted every once in a while by somebody new saying, yeah, I'm working on this. This is cool.
But the thing I'm trying to say is you could feed a coil two ways. You could feed it your signal, your square wave, whatever, or you can feed it the reverse signal that a coil creates called flyback and take a signal from one coil, flyback signal,
Yep.
and send
Peter
it
said you
into
can do
another
that with
coil.
a pancake coil. That's kind of like basically what this is, Peter. It's a different version using more of a sacred geometry, though. But that's basically what I mean. They based Daniel and Erica Nunez patent is based off of the pancake coil by Tesla.
Yep, you can see it. You can totally see it because Tesla's pancake is a bifilar and it's high voltage.
Yes, he was onto something by twisting those wires together. There's some kind of induction method going on. I don't think I fully understand it, but it's drawing in extra energy from the vacuum somehow.
Well, the
It's
more
awesome.
turns the coil has, the more pressure you need to give it before it blows up. The more pressure the coil can handle, and the more pressure the coil will build. And when you release your pressure from it, that pressure comes back inverted, the same amount of pressure that you gave it. So that's why when you have more turns and more wire, you get a bigger spike, a bigger peak on the voltage of the spike. The peak of the spike peak voltage is greater, meaning, not 300 volts, but 800 volts. The more, but if you're, keeping the gauge the same, you can't change the gauge here. When I talk about 100 foot of wire, one gauge gets you a 300 volt peak, and 100 and 500 feet of wire of the same gauge gets you a higher peak.
Right.
Actually, that's reverse. That's why Tesla coils have a thick wire primary and a skinny wire secondary.
No, I'm saying the same gauge. 100 feet of the same gauge gives you 300 volts, and 500 feet of the same gauge gets you more voltage because it's more pressure. The coil has more resistance.
Are you talking about turns of wire? Or are you talking
the more
out?
impedance the coil has, the more pressure it requires.
That's correct. There's a rule of thumb, Ben, and Mike already knows this, but
Ohm's law.
if you have one wrapping of wire on a primary and you have 10 wrappings of wire on the secondary, then you're going to get an increase of 10. It has to do with ratios.
I think this is, and I don't know if you guys feel the same way, but I think that's why the Rodin coil makes a perfect addition to the Bedini SG or Bedini circuits in general, because he's using, the traditional step up method for transforming the energy. And this is using sacred geometry, which transforms it on a 1-to-1 ratio and utilizes that extra energy. So I think, I feel like this is like the next step in his circuit designs here is adding the Rodin coil. I think that's the end result for maximizing the efficiency of his system, in my opinion.
I agree. I think you're
on.
honest.
What I think the Rodin coil is doing is, since it's got that geometry, it's creating that extra negative portion in the spike, which I don't see in a standard coil.
Yeah, you're right, Mike. It does. It creates that extra negative, like you saw on the waveform of Mike's oscilloscope. It's like huge spike on the bottom.
Right, and I have a video where I'm using a standard coil, and it's the same waveform, but it's at the positive side.
Oh, huh.
You're not hearing me. I'm saying the negative side of the spike is way down there. If you look at the signal, I've never seen that, not in my lab.
Yeah, we get some weird stuffs on the scope, man. I'm seeing.
I mean, all that negative spike portion was that's interesting. You can do a lot with that. I mean, you can do a lot with the positive spike portion too, because it also has a small negative portion with it, like you see in his signal here with the small positive portion that you can see in the spike. There's a small bounce in the positive above the zero line, but most of it's below the zero line in the spike in his image here. That's got to be the coil, the geometry of the coil. In my opinion, that's what it is.
I agree. Hey Ben, Mike, do you guys mind if I go through the questions here real quick in the comments? Just don't want our peeps to feel like they're not being answered. Thank you.
Yeah, every once in a while we forget to pay attention to the chat. We get so engaged.
I know. I do the same thing. Thank you so much, guys. So I'm sort of in the middle here, but I seem to see some questions. Let's see. Resonance, in my experience, is the smallest input versus the biggest output. Johan Reader, that's a good way to put it. My favorite way to say resonance is that it's the least dampened frequency or the least dampened signal. I heard that somewhere, and that was a really good description.
Right,
What
I
do you
like to
think,
think of
Ben?
it
What do you
as
think's a good
no
description?
signal attenuation.
Perfect. How about you, Mike?
Right. You don't want any feedback coming in. Well, if you have any feedback, it's going to be the flyback, obviously. But if you have, and you're not going to have any feedback if you're utilizing the flyback or throwing it out.
But there's no flyback in the ZBS, so
I didn't know you guys were talking about the ZVS.
just resonant frequency is where the least attenuated signal. I like Ben's
Right.
too, or least dampened.
You're going to get attenuation when you have feedback. Right.
Yeah. All right. Looks like we have another question here. Let's see. Look for high or HFE current gain values on BJTs. Results in sharper on-off curve slew rate for good spikes. That sounds good for some of the circuits.
Where are you reading this?
The comments on the right.
Up higher or something?
No, toward the bottom. Peter Half Effect says bifilar pancake coils work a lot like that. So yeah, just like when Mike was pulling his smaller Rodin coil to his larger one, it works just the same way as a bifilar or a Tesla coil. Let's see here. Wizard of Woodstock says Jewel Thief is blocking a blocking oscillator. I'm not familiar. I'm not intimate with the Jewel Thief, so I'll have to look into that. Thoughts, guys?
I couldn't. It must have been a trick question. I couldn't get it. Where are you reading though? I'm trying to find where you're reading.
Wizard of Woodstock. Jewel Thief is blocking oscillator toward the bottom.
I'm not seeing nothing. Why am I not seeing?
Are you switched from private chat to comments up in the right hand corner?
I'm in comments. Yeah, it's just not. All I see is LCR meter from Wizard.
Maybe you need to reboot, huh? Maybe it's stuck. Bernie is asking Shawn, please show the coil you are winding. I don't know. Should I? I'm winding many coils.
Show it. Show what you got.
Scroll up.
Oh boy. Can you guys chat for a bit? I got to go pull up my latest coil real quick. I'm almost through the chat here. If you want to take over, Nathan or Ben.
So
yeah, I'm
Nathan,
here.
I was gonna say this modified Jewel Thief circuit. It seems to be good news for our bigger coils. We might be able to get them to work with this thing.
The one you're looking at?
Yeah. Hopefully, I'm hoping at least. But he's using a big coil with big spacings, to as his primary coil. So I'm kind of excited about this. I think we can do it now with the Joker and the Fireball.
I can't wait.
Yeah, this is cool.
Yeah, what is this circuit for, BD?
Yeah, it's a modified Jewel Thief circuit to work with the Rodin coil. So you can see channel A and channel B there. And I believe it's using the open circuit method. I haven't analyzed it thoroughly because I can't sight read circuits yet, but it looks to be using the open circuit method. And he put in 14 volts. And
what I see here in the circuit is the primary battery is triggering the transistor and loading the secondary or the other coil. I don't know if it's the secondary, but you see the one coil on the left is being used to create a trigger signal to the transistor to then send power from the same battery to the other coil on the right to create your high voltage flyback, which will then simulate AC because it reaches over 120 volts. And AC devices will run off of that signal as long as it's got some decency to it, I guess, and it's not too high a voltage. And You know, if it stays around 100 to 200 volts fly back, it should run an AC device because it's not a lot of amps in there. You know, it's not going to run an AC device that has a huge load unless your MOSFET can speed up the frequency and on that spike signal. Or yeah, these jewel thieves. I built one. I made a out of a Makita case. I put it in there for a hurricane that was coming up, and I actually used it when the power went out, and it was impressive, man. That thing was lighting one light. I just used it for light every night on lead alum batteries, and that fit inside the same case. And it ran for like 2 weeks. That one light, it was like a 7-watt light or something, and I had it running about 4 hours a night, 5 hours a night. And it
The
just
power
kept running.
source on that.
It never went out actually. Before the power came on, the power was off for like about a week and a half, I think.
You have like a 12-volt battery or something?
It was like 3 6-volt batteries, lead alum batteries, charged that way. You know, not a dense charge either. You know, 18 volts. I was running it with 18 volts, and one, you know, around a nice big piece of ferrite core. That was one thing I could say. The core spanned the case was about 1.5 feet wide. You know, your standard drill case or whatever. From Makita, and it was about as wide as the case, a little bit shorter, so it could fit in there, and I could close it. I had a plug facing out on one end of the case, and a switch, and yeah, I still got it.
All right, Ben, is this PNP you're looking at?
So it's PMP, but I asked Michael about that, and he said he's using an NPN.
That's a PNP drawing.
Yeah, and he said he's using an NPN and it works fine for him.
Well, it changes the flow direction of everything. You know that, right? Because when you start looking at the transistor here, the arrow on it tells you which way the flow is. So a NPN would be opposite. It'd be on the top.
Yeah, the emitter and the collector flipped or whatever.
30557 MJE.
The positive goes through that first coil, meets the base of the transistor. The negative of the battery meets the emitter of that same transistor to trigger it, and it takes time for the positive to go through that coil and the resistor.
What is that little line going through the resistor symbol? That little arrow. Does that mean anything?
It means it's a diode, or excuse me, it's a light LED. It's a LED diode.
LED. Oh, okay, so that's one of those high voltage LEDs? Or is that
what, to the left on top of the battery?
I'm trying to figure out what kind of component I need to put there. It says 100K.
That's an amp meter.
Oh, hold on. Let me look at it again. Just give me a second. I'll probably pull up a chart. I'm trying to find this thing first.
Oh, I see. Yeah, no. I see the amp meter though. It's the one connected to the base of the transistor. I'm trying to figure out what that is. It's a resistor.
Oh, that's a potentiometer.
Oh, potentiometer.
What is that? I can't see, but
100K.
Yeah, that high resistance.
That's how you tune it. Yeah.
Well, you don't let not too much current go to the base, because if you do, then the collector emitter is going to pass about 10 times the amount of the current that you gave at the base to the emitter. So whatever.
Right, but I'm thinking, because I watched a video with Daniel Nunez in the circuit, and he has a potentiometer, and he's trying to adjust it to find the sweet spot.
Right. The sweet spot for the battery to be handle a load for that coil is what that is. You
right. Resonating with
You want that battery to be comfortable with the coil and the amount of energy the other coil is demanding on it each event of the switch. And the battery is part of the resonance here. The whole circuit has to be in resonance. Not just the coils. Even the transistor, you can't overrun the transistor.
Okay, it says NPN on it for what the model number is. So
yeah, I can't. I need glasses.
No, it's fine. Ben, this is just basically throwing resonance back on top of each other for each coil. That's all this is.
Okay, so it's feeding it back into the coil.
It's not much different than Gerald circuit.
Yeah, I know. I think Gerald mentioned that he did use a modified Jewel Thief, so this might be very similar to what he's using. Yeah.
Yeah, because all you're doing is redirecting the flow back into the other coil.
I mean, if you notice the flow,
Right, and you're using the potentiometer to find the sweet spot of the resonance, right?
Yeah, that's a potentiometer, I think.
Okay.
Yeah. Yeah, that is a potentiometer. I'm sorry, I can see it now.
It's
There's
okay.
a
It's still
resistor and then the arrow, so a potentiometer.
if
And
you
it
notice
looks
the
like
positive of the battery, it's on the left there, flowing up the top of the
100K.
coil down, and it comes back up from the other coil up in the opposite direction. That probably plays a role in the self oscillation of this thing, getting it to self oscillate without a capacitor or nothing like that. I don't see a capacitor there.
Now the only difference is the two coils here, they're not set up how Gerald's is.
And what I'm saying is the flow of
They're not set up
energy
the
is
same way as
going out
yours,
the
Ben.
battery on the left side. The plus terminal is on the left. It's going on the top of that coil down the coil. And then once it triggers the that small amount of energy going down triggers the transistor, goes out the emitter. But once that transistor closes, then the energy comes up the other way, up the other coil, not down. It goes up, I think. I'm looking at it here. You see plus. Then
No, the flow path is right. It's
yeah, it goes up because you see it's tapped to the positive there to feed the other
You
coil.
see the two inputs, the
The
start.
flows are in two directions on the
The
two
two
coils.
starts of the coil are connected along with one of the ends of the channel B of the coil as well. That all three of those ends of the coils are connected to the same line.
If you follow the positive terminal of the battery, you see that tap going on the top of the coil in blue where it says blue, that wire pointing down, and it goes across the other side down and it goes back up the other coil. So the energy, the positive energy is going up, not down, up on the right side of the coil. And it's the energy is going down on the left-sided coil. The positive energy from the battery is going down on the left side coil. and
Oh, I
up
see.
on the
Yeah, no,
right
no, you're
side
right.
coil.
It's not 3 points connected. It's the start and the end of the two channels are
Opposite
connected.
flow.
Yeah, the start of the blue is connected to the end of the brown.
okay. So look,
Yes.
the only thing you need to know
You
is
got
that the potentiometer adjusts the resonance in the coil, okay, to resonate with each other. That's it. It's a self-resonant circuit. That's what you're getting here. Okay, that's what you get. Wizard of Woodstock is absolutely right.
Yeah.
Self-resonating. It's self-resonating between the two coils. The potentiometer controls the amount of flow so that it can do the resonating. And yes, it does work. Okay. So it is not the same thing as what Gerald had. Gerald is working with back EMF. I don't know that this one is at all. Okay, this is
Hey,
just
get this, though.
resonance between the two coils.
Brown,
Yeah, it's weird.
Brown, get this, if you could see the wiring, Brown has a constant 12 volts across it. I do remember that actually from replicating this. Brown has a constant 12 volts across it. Look at the wiring. The plus is constantly connected to the wire, and so is the minus. You'll see it.
Okay. All right.
It's
This
right
is more
there
like
in the middle.
yeah.
It goes down to the bottom, to the left.
So hold on. Let's just stop this madness right now. Ben, Gerald's got the circuit for you, the work, you got the parts. Okay. Figure it out.
Maybe I'm wrong.
Let's
Maybe that's
let's stop moving on to different circuits every time. Let's just figure one out and go with it. Okay. All these different circles will drive you nuts.
Take that back. There's a hoop over there. I couldn't see it. Yeah.
I
It's not
follow you,
connected. Never
Nathan.
mind. Never mind.
Yeah, I don't
It's hard
I
to
don't like
see.
all
You got to
that.
maximize those schematics when you bring them up. It makes it easier.
Yeah, well, yeah, I could see it very easily. Yeah, it's just a big confusion, especially if you
good
don't
for you,
understand the
Nathan.
circuits yet. It's just piling the crap on top of your head. It's just not helping. So
I was actually
yeah.
referring to me, so I could see it better.
No. All I'm saying is stick with one circuit, get it to work. Then you can move on to the next circuit, but don't jump around.
Yeah, I actually got the Jewel Thief working. It's not that hard to build. It's very
I'm
easy.
almost there, Nathan. I'm transferring some pics.
Right on.
Now that you taught me how to share my screen, I can start pulling stuff up.
Huh.
Awesome. Yeah, you taught me a lot today. I appreciate it.
Oh, you're welcome.
I'm going to be a pro here.
Huh.
Ready to finally start my channel. Oh, my goodness.
Well, trying to get you there, man, because everybody wants to see your stuff.
I appreciate it. I feel like this opportunity you've given me here is really breaking the ice and kind of teaching me the ropes. So I really appreciate these Wednesdays you let me share. And thank you too, Ben.
Of course, anytime.
So
Time I'm going live, I usually send out invites just in case anybody's available.
I just saw yours, Ben, in the email. I apologize. If I had a little bit more of a schedule heads up, I definitely wouldn't mind joining. I like the stuff that you're doing.
No, yeah, you don't need to apologize. A lot of the stuff is last minute. That's why I send out a lot of invites, because I expect not a lot of people to be able to show up at last minute.
But when I can, I do, though.
Hey, Ben, I missed that email from the Rumble stream. I got the email
to the
late.
Rumble stream. I thought I did.
Yeah, it was yesterday.
That's why I didn't see you there. I was like, where the heck is Mike? I'm pretty sure I sent you an email.
No, I got the email, but I don't know. I think I was sleeping or something, or just didn't see it in time.
Oh, you missed it. Oh, okay. No. I was like, where's Mike at?
Rumble.
I don't know how to use Rumble.
It's
I
all
can't
free.
figure it out.
YouTube's free. Rumble. I think Rumble though is better.
Every true wizard has a voltage doubler. Victor
If
just
you're gonna
said
start a channel, Shawn, you don't want to want to start with YouTube because they're censoring everybody. That's what I heard anyway.
I don't know how to use Rumble.
It's okay. What Shawn does is not going to get censored. Trust me, he's good. He's building testicles and circuits for him, and you know what I mean. He's good.
Thanks, Nathan.
Yeah.
Or whatever, the copyright strikes and all that. Does Rumble do that too?
Yes.
Oh.
So
nothing exciting. I'm just going to move my current coils here in a folder, and then I'll share them with you guys. Just a couple things that are on my shiny new list. And it's just coils. I'm not going to get into the circuits yet because I feel like we've got a lot of circuit overload tonight.
Yeah.
Ben, any good questions in the chat?
This guy asked, are you guys on Rumble? We are on Rumble. Nathan and I both have a Rumble page, and I know Bernie just created one as well, the Crypto Alchemists. I think it's linked in the description. Let me make sure. Nope, we'll be posting those in chat momentarily.
Oh man. Anyway, all right, Shawn, you got that thing about ready to present?
Yeah, just sorry, not 1 minute. Almost done.
If you need a few minutes, we can play an episode of Cracker Jacks.
What? Oh man. All right. Well, this is what I got. If you don't mind, I'll share my screen or
Yeah, do it. I'll
share
put you up.
my let's see here. Oh boy, you just taught me this. Let's see. Okay, here we go. All right, I'm going to go to present and share my screen. Let's see, entire screen. Make sure nothing's personal showing up. Okay, good. Oh, I forgot to do that one thing. Sorry. There we go. It's a lot. All right, here we go. This is where my dyslexia is my worst enemy. Okay, can everybody see my desktop? You guys see my bank account info and all that?
Yep, got your password.
All right, so I'm in the works of 3D printing this. It's going to be basically a donut jig, but I'm going to use it to create this exact pattern. I think it's in the rodent family, but I'm going to have something close here pretty soon, but this is how I'm hoping to wind it. I guess it's kind of a vortex coil too. What do you guys think?
Yeah, well, it should definitely do that magnet.
Well, it's going in two directions. Wait, you got two vortexes.
Yeah,
two directions.
Awesome.
You do have an interference pattern there, so you're gonna have two counter-rotating fields.
That sounds great. Way cool.
What do you expect to happen there? Cancellation or something else?
Black hole. I want to create a black hole.
They should condense on top of one another to create a desktop black
answer.
hole. Yeah, vortex coils do that.
We like talking about holes.
Oh,
This I just got this cleaned up out of the 3D printer. It's actually an iridescent gold, so this picture doesn't do it any credit. But what I'm doing here is I haven't decided yet. Litz wire or soldering the ends of the Litz wire, so it's one wire, or using like a spool over here to the left and coiling until I lose my sanity. So I haven't decided yet, but I have a whole new respect for people who wind coils like this. Ben, huge respect, because this is crazy.
It's a lot of work.
I had to wind one that was literally maybe 3 inches across, like a small one. It was very hard.
You can end up in a madhouse building one of these things.
It's funny because it just like springs open and you lose all your work. And I know super glue helps, but
it's basically how I did it with the small one. You have to super glue it, but I didn't use super glue. I used UV glue because it's easier to remove if you make a mistake. But it's solid enough to help you, you know.
Good points. Thank you. Also, Nathan's a natural coiler. It makes me sick.
Yeah, I love his Joker coil.
I did too.
You already built a vortex coil, Nathan?
Like Ben's?
Yeah.
Yeah, I did.
You did? I didn't see it. I never saw that.
Oh, here, let me move some of my stuff. I'll grab it for you.
Yeah, his glows in the dark. It's really neat.
So
well,
this is
I thought that was the frame for it.
Yeah, the frame does.
So can you guys see this next slide?
Yeah, that looks like the Death Star coil frame.
Yeah, this is sphere number 2. So this is version 2. It's the iridescent gold because I like the print, and I'm doing it on 33 gauge instead of 32, so I should get a little bit higher voltage. So I can't wait. I'm excited to finish that one. There it is in its form. So a lot of sanding. A lot of people think you could just print this and go, the spheres, but no, you could see it kind of has a rough look. It needs to be glued straight. It needs to be swept through with a piece of sandpaper, and it's all labor of love. But this is a complex thing, so it's not just going to print the first time. So I think that's it. I think that's just a handful of coils right now. Thanks for letting me share.
Thanks for sharing with us.
Appreciate it.
So for those who don't know, this is my coil.
It's so cool. You got to show it in the dark.
Yeah, well, I didn't put it outside to charge up yet.
So it's huge.
Yeah.
What's the diameter?
It's the same as Ben's, kind of the same size.
Yeah, same exact size as the Fireball.
Yeah. So they're twins. They're twin coils. Only.
Yeah,
you mind if I ask how long that took?
It's insane.
This thing came out, by the way, in 20 gauge. Is the best look for this thing, and it's thick and it's nice, and I could push a ton through it.
Yeah, I like the fact. I think 20 gauge is probably more of a fit for that coil size. I use too small of a gauge for sure for that frame. I'm gonna have to rewind it.
What'd you use,
But
Ben?
I will. So I used the 24, but that's all I had available, honestly. So
Just means you have to wind for a whole nother half of your lifetime.
well, I was planning on rewinding it anyways at some point, but you know, if we can get it working, you know, who knows? Maybe I'll keep it the way it is and just make a new one, you know.
Sounds good. All right, gents.
Yeah, it's getting late, guys. So look, Mike, you got that video. We're gonna play it on the way out, and when it's over, we're done for the night.
Yeah, give me a second. Hold on.
Hey, great seeing y'all and spending time with you guys. Great to see you. I'm just going to put myself on mute for the video. Thanks, Nathan, Ben. Thanks,
Hey guys,
Mike.
thank you, Shawn, for showing up and doing everything. I really appreciate it. And well, I'll see you. To probably talk to you tomorrow.
Awesome.
Thanks, Shawn. We appreciate you.
Awesome. Thank you, guys. I appreciate
Thanks,
you
Shawn.
guys. Bye.
Mike, this is the captain speaking. Have you and Ben been able to fix the transporter yet?
That's what I'm saying. I can explain to you very simply how to verify if that ground, the third prong at the bottom, the circle hole. I think it's 3 prongs, right? 3 holes. You're in Canada? I don't know.
No. It's 3 holes. Yeah.
So you have the ground. The third hole is the ground. So you could test that ground by. You have the 2 other holes. Are they the same size or is one bigger?
I'm sorry. Say that again.
You have 3 holes. One is ground at the bottom, and the 2 that are at the top are the power. Are they the 2 holes? Are they the same size, or is one bigger?
No. They're the same size.
Same size. So it's 2. You're in Canada,
No, Michigan.
Michigan. So it can't be the same size. One slit is a little shorter.
Are you sure? Let me see.
Look closely. You need more light in there.
Oh yeah, you're right.
I'm sorry, Mike. Did you say you had the transporter fixed?
Put the voltmeter on AC 120 volt setting. Put 1 prong in the ground and the other prong in the smaller hole. That's your hot line. And if you get 120 volts, that ground is working good. If you don't, you get less than 120 volts, like 90 or 80, your ground is probably no good on that plug. That could cause a lot of issues for the circuit too, by the way.
Well, the problem is this only goes up to 10 amps and then it blows.
No,
so-
you don't need amps. You just need 120 volts. Is what
It blows.
Okay. As long as it doesn't blow my fuse.
Put it
I'm
on
good.
volts, not amps. Volts. 120 AC volts.
This should be good to 250 volts, so we should be okay.
Hey, Gerald, come here and listen to this. I can't tell if they're fixing the transporter or not.
Right. So now put 1 prong in the ground, the other prong in the smaller hole, not the bigger one, the smaller.
Does it matter which one is which?
It, no, that's too much. It kind of does matter. But anyway,
Wait, so the red
of the 2 holes, other than the ground hole, of the 2 holes that you have there, one is smaller. That is the smaller hole is the power. The bigger hole is the return for that power.
the negative. Okay.
Yeah, you
So-
don't want to use that to.
All right,
check
so
this out. You wanna
real
check
quick
the
before I
power.
electrocute myself, Mike, which
You're not going to.
hole do I stick this in?
Don't stick the plug out. Just stick the prong.
hole is
red, there's
wrong.
The probe has two prongs, 2 metal.
I'm sorry.
Put 1 prong in the ground and the other prong in the smaller of the 2 holes that are left.
But it doesn't matter which one is which.
No, it does. One of the probes, you have 2 probes from the voltmeter. One goes. No, it doesn't matter which one of the 2 goes in the ground. No, it doesn't.
Okay,
Yes,
so I can put the black one in the ground and then
Yeah.
the red one in the
Yeah.
small slot.
Yes. Sorry, I
Okay.
misunderstood you there.
No, it's okay. We're talking about putting things in holes.
Yeah, easy to
It's your
get.
probe, Ben prefers a certain one.
So yeah, if you don't see a 120 volts right away, just wiggle it around till you get a good connection. You just see either 120 volts or like less than that, like maybe
It's just
100
too
volts.
easy.
Yeah, 120.
Okay, your ground is good. You just verified it. It's good ground.
Nice.
Now, just so you know, if it read less than 120, like around 100 or 90 or 80, that ground is no good.
Oh,
Right. Okay. It was actually slightly above 120. So is that normal?
Yeah, you're
It's
good.
like
You're
120.
The ground is good. Good. Just make sure you're firmly connected to that third prong into your circuit.
something tells me we're never getting this transporter fixed.
If you were to put one prong into ground and the other prong into the return, you wouldn't get anything because it's not torch. You're not hitting torch. You want to go from ground.
Oh my God.
Torch to ground to get it.
Oh,
No, that makes sense. If you're
Oh.
not properly grounded, you're going to be getting a loss.
You're right, Nick.
yeah. Oh my Jesus, guys. That is so great. Guys, thank you for hanging out with us tonight. Mike, thank you for being such a good sport about this, man. It's so amazing.
Thanks for having us on.
Thanks, man. See you, man.
Later,
See you
Mike.
guys Friday.
Yeah, I'll see you guys for Free Energy Fridays.
All right, guys. Yeah, see you on Friday. Have a great night. Thank you.
Thanks, chat. Thanks, Nathan. Later, guys.